So today, children, we are going to be learning about buffers and networking and threading and mutexes, I think. Only the basics, because that's all I know right now. So we're going to start with and this assumes you know C++, like you have at least watched the previous tutorial. So we include IOStream, we have int main, and we return 0, the most simple program of them all. And so what we're going to do as our first thing is we are going to include another header. This header is going to be fstream, but I'm being dumb and not putting include. fstream. There we go. Now fstream is just like IOStream, and I think even the classes inside of it are derived from the same classes as IOStream. But fstream is like IOStream. It has functions similar to stdcout, but instead of stdcout, instead of the standard out stream, we have file streams, and these file streams are just like cout or just like cin, except they're streams that point to files. So in this case, we're going to have ifstream, and ifstream is a file in stream. So it gets the contents of a file and puts them into something. So in this case, we're going to have a std ifstream object. We're going to call it R file, and we're going to give it a constructor right here. This constructor, or well, we're not going to give it a constructor. We're going to pass into the constructor for this first initially the path to the file. So test.cpp, which is just this file that I'm writing into right now. So we're going to have test.cpp, and then we have to specify the mode that we're opening it in. And all these modes are different types of perhaps enums or something like that. I'm not exactly sure. They're different types that are defined within the fstream file. So what we're going to do is we're going to say std fstream in right here. And so this is saying create object std ifstream called R file, pass into the constructor test.cpp, or the path to the file that we want to open, and then right here the mode that we're opening it in. And right here we're opening test.cpp, which is this file right here. We can find it right here, test.cpp, and we're opening it in mode, which allows us to read the file. So what we can do is we can say we can create a new variable as well. Just call it we're going to have std string word, or I'm going to actually have it set to read. And then what we're going to do is we're going to say R file read. Oh, like this. Then we're going to use std cout read. So what this should do is this is going to create the ifstream object. It's going to push whatever is the contents of the ifstream object into read. Read is a string, and it's going to push read into the outstream. So let's see what that looks like. So we get hashtag include. The reason for that is this operator right here for the read, for the R file, it will only push text up to a white space character. So once we hit the white space character, then it will stop pushing text into a read. Right here. This works just like cin, except for instead of putting stuff inside of cin, instead of typing whatever we want inside of cin, it automatically knows that the stuff inside the stream is just the text inside this file. This file in this case is test.cpp. If we check what test.cpp is, well, it's the file that we're currently writing. So what should happen when this opens this file? Well, it's going to open this file, and it's going to push the first, all the characters up to the first white space character into read. So what is that? Right here, it's going to start, it's going to get hashtag include, and then it hits a white space character. So we will no longer push anything into read. Once that's finished, it's going to push read into the standard out, and that's it. Right here, we see that this is this IF stream mode, or this is in mode. There's also different types of mode, like out mode, which is if you're writing out to a file. In this case, we're using an IF stream. IF streams don't write to files, so it's not much of a reason to use out or append or anything like that. We're just going to be using in for this. Now we're going to specify a separate mode. This mode is going to be binary, or well, standard IF stream binary. You can also just use OF stream in and OF stream binary. And OF stream is like IF stream, but it's the out stream for files. It's the out file stream. And then IF stream is the in file stream. So this lets you write to files. It still has the same standard in specifier right here, though. You can just use this same in and binary modes. And what's going on here is we're using this operator right here. This is the bitwise OR operator, and what it does is it takes the type that's on the left, so whatever this is, I don't know, it's defined somewhere in the standard library, but it takes this type, it takes its bits. So if the bits, for example, were, we're going to make this pretty simple. 1111. Well, actually, I'm going to say that the bits are going to be 01, 01, 01, 01, 0000, 0000. And then we're going to have another, we have another mode right here, which is binary. And let's say this mode's bits look something like 11111111 1000000. What this will do is it compares the bits for the in type right here. So it's going to take this in type, which we're just arbitrarily saying that maybe the bits look like this in this in type, for example. And then it's going to take this binary type right here, and it's going to say, all right, the bits maybe look like this in this binary type. And it's going to say return this in a configuration where if either of the bits are a 1, then return it as a 1. So what it's going to say is for every single bit, pretty much, it's going to say if the bit in that position for in is a 1, or the bit in position for binary is a 1, then you want to return a 1. So in this case, we're going to return all 1s right here because we got a 1 in every single one of these positions. Then I'm going to say, all right, well, which do we return? Do we return a 1 here? Well, either of these have to be a 1 in order for this to evaluate to a 1. So yes, we do have a 1. And then these are going to all be zeros, because neither of these are 1s. So this is the bitwise OR operator. It changes the bit to a 1 if either of the values on the left and the right side of it are a 1 in that position. There's also the AND operator, which only returns a 1 if both are a 1. So the AND operator in this case would return a string that looks like, or would return binary that looks like this. And that looks suspiciously similar to this first one. That's what that does. It was just decided that for IF streams, the modes should be decided with some type of data type that is represented by some type of binary that is parsed by the makers of this library. So when you're deciding the types, you want to put this bitwise OR operator to say that you're using this type and this type, because that's just how it works in this library. So now we have a string called read, and we're pushing the contents of our file into read. And remember, we only got hashtag include because it did it only up to the first white space character. Well, how do we get more than just up to the white space character? Well, what we can do is we can do our file. Actually, I should have kept that. I think it's our file dot get line. Yep, like this. Oh wait, before I do that though, I changed it to binary mode and I didn't show what happened. So let's see what happens in binary mode. So in binary mode, or in the default character mode, it gave us up to include. In binary mode, let's see what it gives us. Up to include. So it's the same thing in binary mode right now as in default mode. If we check, just include. Let's keep it off of binary mode for now. Let's do our file dot get line, which is just, you know, a class member function of this. And we're going to say that within this get line function, what we're going to do is we're going to specify first the I think it actually may only be, well, let me see actually what this is asking me for again. So it's asking us for a character, a pointer to an array of chars. So I think a string would be valid in this case. So read, and then also how many characters do we want to read. So in this case, we're going to read up to 1,024 characters. No instance matches the arguments list. And that's yelling at us because read is not an array of chars. Let's just make it an array of chars so it stops yelling at us. So right there. Now it's not yelling at us anymore. Now it says include IO stream. Well, that's because the get line function gets one single line and it pushes it into an array of chars right here, and this second parameter says get up to 1,024 characters. So that's very simple. If we put this into binary mode, let's check what happens. Let's copy this and just replace. See, we get the exact same thing, except for why is there no hashtag there? That's a little bit strange, actually. I'm not entirely sure why there's no hashtag, but it's probably why when you're going in binary mode, you don't want to do weird stuff. You want to treat the objects like binary if you're going in binary mode, probably. So we don't have a hashtag there. In binary mode, what this is saying is get up to 1024 bytes instead of 1024 characters. 1024 bytes in this case would be a kilobyte. So that's how you get one line. You could put this through a for loop and get all the lines if you wanted to. But that's not really, I don't much feel like doing that. Now, we kind of just created a buffer right here, this char read. If you know anything about a char in C++ actually is a data type that only takes up 1 byte. So every single char will be exactly 8 bits. And so what that makes it ideal for is chars are ideal for representing binary in C++. You can use other types like a uint 8t, but and what this is this is just a integer that is only 8 bytes, and it's also unsigned because this u is unsigned. This int 8t is just a signed integer with 8 bits. So you could use something like that to represent binary or bytes in C++, but most people just use an array of chars, and because chars are by default 1 byte or 8 bits. So what this is saying, this char would actually more properly be named buff for buffer, because we're creating a buffer right here almost. And within this buffer is 1024 bytes. It says char, but every single char is 1 byte, and so it's going to be 1024 bytes right here. When we're saying get line, we're getting 1024 chars, and actually this is also just like getting 1024 bytes because every single char is a byte. And we give a pointer to buffer in the beginning. You can also, as buffer, use like a vector, or what I'm actually going to use right now is I'm going to include something else. Include array, and this will let me use what's called a standard library array. So we're going to create array. We're going to give it a type of char, and we're going to say that it contains 1024 characters, or 1024 bytes. So this is just like a standard library vector, except it's kind of like a fixed size vector. It is like when you reference its name, it does not provide a pointer to an array of chars. It doesn't provide any pointer, it just provides the object itself. So in that case, if you wanted to get a pointer to an array, because a lot of different functions are assuming when you're using an array you need a pointer to an array, you use buff dot data, and you just get, this returns the pointer to the array that the standard library array actually uses to store its data. This template also right here, if you remember what vectors you needed to put in the data type, since arrays are a fixed size, the template requires you put in the data type and then a size. So right here the size is going to be 1024, and we're naming it buff. Something also nice about standard library arrays is they provide you with iterators, so you can use array dot begin or buff dot begin. And that will provide an iterator to the beginning, and if you use buff.end, it would provide an iterator to the end, which is quite useful. So I'm just going to use a standard library array as my buffer in this case. What we're going to do is, let's see, rfile.getLine. Well, now it's yelling at us because this buffer is not it's not a pointer anymore, because remember, only default C++ arrays return pointers. So in this case, we're going to say dot data, and this dot data will provide a pointer to an array that this buffer uses to store, and that array will be an array of chars, because this array right here stores chars. So right here, what are we saying? It says push buffer into cout. Well, that's because buffer is no longer an array of chars, so we cannot push it into cout. We need to push, well, because cout doesn't understand the buffer, doesn't understand what a buffer object is. Cout does, however, by default understand what an array of chars is. It treats an array of chars pretty much like a string. So we can say dot data, that will give us our array of chars. It'll treat that like a string, and it'll just cout that. So right here, get include IO stream. So if we put this in binary mode, we'll also see some stuff. So binary. This does the exact same thing. For some reason, it skips the hashtag in the beginning. Not entirely sure why. But in this case, when you're using binary, you probably don't really want to use getLine. Probably a better function for you is .read. So what .read does is it takes in two things. It takes in a array of chars to store all the data that it reads, and it takes in the amount of data to read. So we're going to still read 1024 chars or 1024 bytes, because this is our buffer and it stores 1024 bytes. This is going to go up to 1024 bytes. That's what this read function is going to do. We're going to say right here, store into buffer.data. Buffer.data is an array of chars, which is going to represent our bytes, since every single char is a byte in size. And so what happens here? Well, we see the include IO stream, include F stream, include array. Well, yeah, that's what we have in the beginning. Into main, yep, return 0, yep, and then this. And then there's this whole giant section of just garbage data. And the reason it does that is because maybe this program only takes up 100 bytes, but we're saying it's 1024 bytes. Read 1024 bytes. Or, well, no. More precisely, we're saying that the array is of size 1024. And all the characters inside of it are just undefined. We didn't put anything in them, because this read function is only reading maybe 100 bytes to it. So to remedy that, what we would do is we would say, instead of just cout buffer.data, we could say perhaps that that this .read function should perhaps write to a file, let's say. So in this case, I'm gonna copy this, make an OF stream object this time. So right here we have an OF stream object, and we're gonna call it test output.cpp, right? And since this is an OF stream object, we're gonna be writing to files. So we don't want to have it in mode. We could have it in out mode, but the issue with out mode is that every single time you write to the file, it completely overwrites the file. It pretty much deletes the file, writes a new file on top of it. So we're going to be writing in append mode this time. So every single time we write to the file, it's going to be adding data to it instead of deleting it and then re-adding data. So, and we're also going to open this in binary mode right here. So now, when we read this file right here, what we can do is we can say, this is actually should not be R file, this should be W file for write file. So we can say W file dot write, and now W file dot write, what this function does is it takes an array of chars as the input, and it takes an amount to write. So the array of chars that we want to write to in this case is buff.data, or that we want to read from, right? Because this write function will write to the output.cpp file that we just opened as this ofstream object right here. So this W file is an ofstream object. We're calling the .write method on it. We're going to say we want to write, or we want to take the contents of buff.data, and we want to take an amount of bytes equal to, let's say for now, 1024, because we know our buffer is of that size. This is an issue, and we'll see why, but let's run this. So this is in append mode. We're writing in binary mode. Let's run this. It didn't give us any errors. Okay. Now let's take a look. We do have an output.cpp file. That's really quite nice. It created this whole file, and we see it's exactly 1 kilobyte. Okay. This one is 356 bytes. So we copied test.cpp, right? Because in our read file, we had test.cpp. We copied its contents into buff.data, and then we copied from buff.data into output.cpp. So right here, it should have been that output.cpp is the same size as test.cpp, but it is exactly 1 kilobyte as opposed to 356 bytes. Well, that's because what we're doing is we're writing the entirety of this array to it. We're not only writing what we read. We only read maybe 356 bytes, but that doesn't mean that the array is 356 bytes. The array is still the full 1024 bytes. So we wrote the whole kilobyte to it. That means we're going to have 356 bytes of good data, and then, you know, the rest of it is going to be garbage data. Let's take a look. Well, what do we see here? We see just a line of garbage. We see all this good data that we just wrote, this 356 bytes, and a line of just garbage that it read for us, and that's not what we want. We want to read only, or we want to write to that file only what we read. So in this case, what we can do is we can use a really quite nice function. It's called R file. R file is our ifstream object that we created right here. We can say R file dot G count, and G count will tell us the amount of bytes that it copied. So in this case, it will copy 356 bytes, and we're going to say write, starting at buff.data, write 356 bytes. So instead of copying the entire 1024 bytes from buff.data, we're only going to copy 356 bytes, because this G count returns, right, R file.gcount. G count will return how many bytes the previous read operation from R file read. So in this case, R file has a read operation right here. It will read, it says it's reading 1024 bytes, but that means it can read up to 1024 bytes. In this case, it'll only read 356 bytes because that's how big our file is. And this G count will now return 356 bytes. And so this buff.data will go up, will only write from buff.data up to 356 bytes. So let's run it. We should see we get a nice little file. So we see, well, actually, yeah, that's 366 bytes now, and that's also 366 bytes. We see this is exactly the same file that we just had now. Perfect. That's what we wanted. Right. Now imagine, though, that we were an expert C++ commenter, right? We loved comments. Let's write proper comments. And let's say that we wrote so many comments. We just love comments so much that we wrote so many comments. Actually, let me have this a little bit more condensed instead of all these spaces. And let's copy a little bit more. So now we see we have a 47 line document right here. Let's save this. And we see inside of here, our test.cpp is now 1.88 kilobytes, right? So let's delete our previous file. Now let's run this, see what happens. Okay, so nothing, no errors. We get this output.cpp, but what we notice is this output.cpp randomly stops only at line 31. We had 47 lines of characters, and the reason that is because our buffer size is only 1024 bytes, so we're only copying at most 1024 bytes when our file is 1.88 kilobytes. So that means that did not copy properly. We didn't copy all the data. So how would we do this? Well, we can put it in a do while loop. So we can say do, and put this in parentheses. And well, if you guys want to know how to tab a whole bunch of lines at once, select all the lines and press tab. To put that back, shift tab. But we're just going to have tabs like this. And let's do that. So we're going to do this while rfile.gcount is greater than 0. And put a little semicolon right there. So now we should run this multiple times until we have, once this has read 0 bytes, we know there's no more bytes to read, and so we stop. The reason we don't use a regular while loop is because if we evaluated this while statement first, what would happen is we would see, all right, what was the previous read operation? None. We don't have any previous read operation up here. So this would equal 0, and this would immediately fail, and we would not read anything. So we use the do while loop to read this at least once. And then we check, all right, did we read greater than 0 bytes? If we did read greater than 0 bytes, then we're going to try to read it again. We're going to keep doing that until we read 0 bytes, and then we know, okay, there's nothing left to read. Let's run this. And gives us a nice little exit bubble. We see now output.cpp is the same. Goes all the way up down to line 48, which is the same as this right here. So now that's perfect. A few other things we should mention is that the read function, what happens if for example, we try to read 1024 bytes, but we only read 356 bytes. What happens is that this R file now has a few flags set on it. It has a few flags saying that, some type of error happened, end of file or bad bit or something like that, that this R file stream is no longer good. And so it cannot read anymore. that happens if you read less than the amount that you put in for this. That's not an issue for us, because by the time that we read less than the amount of this buffer, we're already going to be at the end of the file, right? Imagine we read the file is 1.8 kilobytes. Well, if we read once, right, it's going to read the full 1024 bytes. It's going to be all good. And then it's going to go to read the rest of the 800 bytes left. And it's going to read 800 bytes. And that would be finishing the file. But it only read 800 bytes. It's going to put on the error flags saying that the read has failed in some way. That's not an issue for us, though, because we already read the last of the 800 bytes. And so we just write those. And presumably in this simple situation, this stream is just destroyed. So not much of an issue for us. Other things I should mention is if, for example, we have this output.cpp, right? And we open this in append mode. So in append mode, if we run it again, right? Okay. Let's take a look at our file. Now it's 4 kilobytes. Well, it just copied the contents once again, starting at the same line right here. Interesting. If you've ever seen why people, why do programs leave an empty line at the end of the program, a lot of that reason is for stuff like this. When you're copying stuff to a program, you don't want the stuff to start right here. You want it to start on the next line. And so people leave an empty line, usually, to allow more stuff to be copied to that file. In this case, we don't actually really care about, or we don't want stuff to be copied to this file. This file was only meant to be copied once, but we have twice the amount of data in it because we ran the program twice. Well, the way that you would fix something like this is you would maybe do some checks to make sure that the file exists, or maybe initially what you can say is you want to open the file in out mode. But the issue with out mode is that out will overwrite the file on every iteration of this. Every single time we do this write operation right here, it's going to overwrite the file. So it's going to copy the first 1024 bytes, and then it's going to copy the next 800 bytes. It's going to overwrite that 1024 bytes with the 800 bytes. So we're only going to get the last 800 bytes. So if we go right here, this is our test.cpp, we want the output. Well, actually, that was not supposed to happen. Huh. Maybe that's not such a big deal. I don't know what it is. Oh, you know what very well may be happening? It may be that this out thing keeps track of its position in the file. So if you're running this out or this file in out mode on the same program, the same cycle, it's gonna properly keep track of where it is in the file, and it's not gonna overwrite itself. But what happens if we create this file, right? We created this file with that previous run of the program. Now let's run this again. Well, it's the exact same thing. It did not append anything to the file. That's because what happened is the first time around on the do while loop, what happened is it went through here and it wrote to the file, then it kept track of where it was on the file, and then wrote the last 800 bytes to the file. I didn't actually know that out kept track of where it was. I thought it just, on every iteration of this do while loop, it would overwrite the file. And so we would only have 800 bytes at the end. But evidently not. What it does do, though, is that if you run it 2 times, 2 separate programs, the second time it's going to overwrite the file you created on the previous program. So this file is completely overwritten because the first time we ran this program, the stream was keeping track of where it was in the file. Now the second time we run this program, the stream, we have a completely different stream to the previous time we ran the program. So now the stream just writes a new file and keeps track of where it is in its file. So that's actually quite useful, because I thought what would happen is when we use this out mode right here, it would overwrite itself even on the same instance of the program, even on the same instance of the stream. That's quite nice that it does not, though. The way that if this I remember saying that this read operation, if it reads less than this 1024 bytes, it will fail to read again. So it'll mark some fails on the R file stream right here. The way that you would fix that is just call the, for example, you could call the R file dot clear, declare the flags on it saying that it has errors, just like CIN, and then you would do like R file dot ignore, and you would tell it to ignore perhaps a kilobyte of information. And in this case, it would clear the stream and ignore it, and it would be ready for the next time you use the stream. This is not an issue in this do while loop I already explained previously. And another reason it's not an issue is since right here what we're doing when we create this IF stream is that we're placing the file path inside of the constructor. We're saying test.cpp right here. What happens is once it gets to the end of the scope right here, it will call the destructor, and it'll destroy the object in this stream. We won't have to care about it anymore once it gets to the end of this scope. So what that would be useful in is if perhaps you had a void copy files function, and this function perhaps it accepted, I don't know, 2 strings for input and output file. So let's do std string input, then std string output, or O right there. And what would be nice, let's just copy all this into here. We don't need to return anything. Is if you had a function like this, for example, you could just say that this right here is I for input, and this right here is O for output. And then you could, I'm just gonna right here, actually I'm gonna delete this, because now that we have this function to copy files, we're just gonna use this instead. So right here, we can say copy files. We can put in a string, for example, test.cpp, and put in for the second parameter the ending string. So the ending string is going to be, or the output string is going to be, output path is going to be output.cpp right here. And we call that function, we put in the file paths, and what this function will do is it'll create the buffer, it'll open the files, it'll do the thing, and it'll be finished. Now, if we had, for example, did something like, instead of this, what you can do is I'm not sure if this will work. No, this does not work. Well, if you didn't specify the modes. But what I was saying is, if you do open and then you put in, for example, the path of the file that you want, this does the same thing as this first variable for the constructor of this object. So this first variable right here is just saying, well, I don't know why I have this as a string to I, but this first variable just specifies the path to the file. This dot open also accepts the path to the file, right? Except the difference between using the constructor and using the dot open is that using the constructor will call the destructor, or will call the destructor when the file is when the stream object goes out of scope. So it'll go out of scope once this copy files function is finished. Once it gets to the end of this function, this R file will be out of scope, and so the destructor will be called on it. The destructor, we'll see that we passed an I for the constructor, and so it'll destroy the object based on that. And so the destructor handles that all for us. Though if we put this dot open, now what this does is this opens the file, and the destructor no longer can do anything about it. We are now in charge of manually calling the rfile.close function. Because if we don't use the rfile.close function, this R file will sit in memory forever. It will be a memory leak. It'll be memory that we're not using. So we would be responsible for calling the .close function. So what's nice here is, since this is just going to go out of scope at the end of this function, we don't need this open thing right here. We don't need this close. It's going to go out of scope at the end of this function. We can just allow it to destroy itself after this function. And another nice thing about destroying itself is that next time we call this function, even if read has errors on it, it's going to be a new stream, right? Because we are calling this function again, a new stream called rfile is going to be created, and that rfile won't have any more error flags on it. It will be a completely brand new rfile because this stream was recreated next time. And that's the nice thing about using the path in the constructor. If we run this, we'll see it gives us errors, and that's because this is not declared. Right here, now we can see that we got output.cpp. We got a nice little file right there. Quite nice. So next, what we're going to do is we're going to figure out how to use a similar method when dealing with stuff like network buffers and such. Alright, so let's get rid of a lot of this. Let's include fstream so that we can copy contents of stuff. Actually, maybe... No, I won't include this copy files anymore. So right here, let's get rid of this copy files function, if I can properly do this. Okay, so we're going to be using a library called asio. So the way that you get asio is you go to asio C++, and you go to here, and you go to download. And this site looks really quite ugly with that extension. You go here. You don't want to get the boost version. Probably just get the regular version, like that one right there. And you can download it. You can put it into, for example, how I did it, So I have it. Let me do this on my other monitor. Alright. I don't want to be showing what's inside here. Alright, so here's my SDKs folder. All I did is I took asio right here. I extracted it to the SDKs folder right here. It's just my SDKs folder. I got random SDKs. And we got a little asio folder right here. And I went into Windows. I went environment variables right here. And I pressed new. I created something called asio right here, as you can see. And I just gave it the path to my asio folder. So now, if you don't know what environment variables are, you can pretty much just use them to reference this specific path. So the path in this case is just going to be the path to the SDK folder of this. So I can just use the name asio as an environment variable to reference this exact path, making it easier to use in like Visual Studio. So that's what I did. So currently we are an online school, so we're going to be speedrunning this. And this is where we start. We're going to be using a library called asio, as we said probably previously. Asio requires some include files, some header files that we include, and it also requires that we define a preprocessor directive. So right here, I'm also going to put include IO stream. I think we're also going to be using include fstream, and we're also going to be using include array. There we go, array. And this, as you can see, these asio files are not being found. Well, the way that we find them is we go to properties and we use our preprocessor directive that we created. I'm going to change the Visual Studio Standard right to here, 2017. And I'm going to go to just C++ general. And now we need to include the include path for the asio SDK. So that include path is asio, and this syntax signifies that we're using our preprocessor directive called asio that we created in Windows / include, because we're going into the include folder of asio. I'm just going to press apply right here. Okay, and now these are fine. So this is asio.hpp, the main header file. This is a buffer.hpp that includes an asio buffer that we're going to be using, asio internet.hpp, which is going to include some classes and functions that we're going to use. Right here, we define asio standalone. That's because, well, if you remember what a preprocessor directive is, it's the preprocessor you can define something with the preprocessor, and then when it's compiling the code, it will compile the code based on whether you have that preprocessor defined or not. So inside of these asio header files, they might have sections of code that are only compiled based on whether asio standalone is defined. And in this case, we're going to define asio standalone because we're telling asio only compile the stuff for the standalone version of asio. If you did not do that, then you're going to get a different version of asio called boost asio, and boost asio is for the boost library, which we're not using. So in this case, we define asio standalone, and then when it goes through these header files right here, it's going to know compile asio to be used standalone instead of with boost. Right here, we're going to be making a function int main, and we create a nice little thing like that. So initially, what we're going to do is we're going to create since we're going to be doing networking, we're going to need an IP. So we can use std string for that. And if you don't know why we're allowed to use std string, let me actually create this string real quick before I say anything. All right, so how are we able to use this std string without specifying include string? Well, that's because presumably one of these header files right here that we included also includes string. I don't know which one of it exactly it is. It might be iostream. Maybe even if we remove iostream, we can still use it because maybe one of the asio ones includes string. And if that's the case, then that means we don't even really have to include string. We can, though, still include it if we want. And string has those header guards. Look at how nice I made that. iostream is the biggest, then fstream is the second, third, fourth. Just looks so nice. So we can use a string because it was presumably included in one of the other header files. Since we're doing networking, obviously we need an IP address. If you don't know what IP addresses are, they're pretty much just like, well, when you make an address to send data to somewhere in the internet, you usually just need an IP address and a port. So an IP address will be 4 numbers, for example, this 127.0.0.1. And this IP address signifies that I'm trying to send data to my own computer, right? And then somebody else would be hosting a service at this IP address, and when they get your data, they can receive your data and they can respond by sending it back to your IP address that you sent from. In this case, I'm just going to be using 127.0.0.1 because that's my computer. I could also just use my local IP address, which is 10.0.1.4, I think. But I'm going to use 127.0.0.1. I could also use my public IP address, but I don't really want to put that on this video. We need another object right here. We need a port, and that's just going to be an integer. And we're just going to set the port to 60,000. So how this pretty much works is very, very simply. This is not a tutorial on networking. This is a tutorial on internet buffers. But we're saying go to the IP address 127.0.0.1, or we're not saying that right now. We're just defining a string that says that. But if we were to connect to this IP address, we would be connecting to 127.0.0.1 and finding whatever service is on port 60,000. You can use whatever port you want as long as there's a service listening on that port. We'll save this though, because I gotta go to my online classes. Okay, now that we have an IP address and a port, those are just strings and integers. We're not doing anything with them right now. We're gonna need to create some asio objects to be able to actually use this library to connect to internet and send data. So I'm going to create an asio object right here. It's going to be in the asio namespace, and it's going to be called an IO context. And this is a object included in asio, and it is kind of like an instance of asio. This is what connects to the operating system and does all the asio operations to send the data. So you need one IO context to allow asio to actually do stuff right here, and a lot of different things are going to be binded to this IO context. We're going to also give this a name, and I don't really know what default values we can give this IO context. So in this case, I'm just going to be default initializing without using any constructor, without using any equals initialization, or that would be actually copy initialization. We're not going to be using any of that. All right, now that we have an IO context, we need to create a little bit of more variables. We're going to say, how about, well, actually, I'm going to create this up here because it will look nicer. We're going to have an asio error code. It's going to be EC, and this error code is, it's an asio error code object, and this object right here is used within asio to handle errors. So instead of crashing your program, asio has some internal functions that just pass on errors to this error code object and save your program from crashing, which is nice. So we can use that error code object to catch errors later. We're also going to create another thing. We're going to create an asio IP TCP socket. And a socket kind of represents a connection. This is going to be a socket that sends or receives data, and this socket will be bound to an address, so like an IP address and a port, and that's where it will send the data. And you also need to give it an IO context so it knows which instance of asio it needs to be bound to. So we're going to give it that IO context right here. We're just going to say socket context. And that means that we're creating an asio not asio IO context, asio IP TCP socket right here. And we're creating that socket object and giving it, passing into its constructor our IO context that we just created. Very simple, very nice. And so next thing we're going to do is we're going to say, we're going to socket.connect to a IP address and port. So how do we do that? Well, this socket.connect function, it's taking our socket object that we just created right here, and we're connecting it, and it wants two parameters. It wants an asio IP TCP endpoint object, and it wants an error code object. We have the error code object right here, but we do not have any asio IP TCP endpoint object. So we can actually create that right now. We can say asio IP TCP endpoint. And this object, it's just an object of that type without any name. And we're going to be pass into its constructor some values right here. So in this constructor, we can pass in values such as, well, what this endpoint wants is it wants passed into its constructor, I think, a asio IP address object. So it wants an asio IP address object. The thing is, a better way to make an asio IP address object is to use a function called asio IP make address. And then you pass this object an IP and an error code. So this IP is just going to be the IP that we created earlier. The error code is just going to be ESC. This wants also a port. So what are we doing here? Well, we're using the socket.connect function, which accepts an asio IP TCP endpoint object. This endpoint object, we're constructing it just on the spot right here. It's going to be a temporary variable that's just constructed and passed into this function. We're constructing it on the spot using an asio IP address object and integer port. The asio IP address object is made using this asio IP make address function right here, and we pass into it an IP string and an error code just so it can catch errors. And then we also pass into the socket.connect function the error code right over here. So you could make these all in separate variables, but we're just constructing it on the spot. This asio TCP endpoint object is just like doing something like, well, I'll show you. It's just like doing something like endpoint like that. And what this means, right, is that we're creating an object of asio IP TCP endpoint, and we're assigning it to this endpoint variable, and we're passing this into its constructor. Very normal, very simple, very nice. So after that, what we can, I should teach another way to do this. Another way to do this, which I hadn't taught previously, is we can say asio IP TCP endpoint equals asio IP TCP endpoint with that passed into its constructor. I don't know why the colors are not changing. It would be much easier if they were. Let's press Ctrl S and they still do not change. What if I close the file and reopen it? Now it's all nice. So if we take a look at what's going on, well, we have an endpoint object right here, and it's of type asio IP TCP endpoint, all right, and we're setting it equivalent to an asio IP TCP endpoint object that is constructed using these variables passed into its constructor. So we're passing into its constructor the result of the make address function and a port right here. Instead of using this asio IP TCP endpoint right here, we could also just use the endpoint variable that we just created over here, if I could spell correctly. We could also just pass in that endpoint object right there. And it's still yelling at me for some reason. Oh, wait, because we don't need a port like that or something. There we go. That's properly how you're supposed to do it. So we could just pass in that endpoint object. I'm not going to do that. There's no reason to really save this endpoint as a variable for us. We don't need it as a variable. So we're just going to create an object of that type right here, construct it on the fly, and then pass it into the socket.connect function right here. Very nice. Something I should say is this right here is not quite equivalent to the previous example. So if I remember correctly how this is done, this is going to be an endpoint 1 object, and this is going to be assigned, or we're not going to assign it. So at the end of the day, these both have the exact same results. This is an asio IP TCP endpoint object called endpoint 1, and we're constructing it using these parameters. This is an asio IP TCP endpoint object called endpoint, and we're assigning it to an endpoint object that was constructed using these parameters. So in this first example, we're constructing a temporary object and assigning it to the endpoint. And right here, we're constructing the endpoint 1 just by default right here without assigning it to anything. There's no copy initialization here. We're not copying anything. We're just constructing it. So a reason that you would use a syntax like this above one, though, is in certain circumstances, like inside of a class. For some reason, I don't know the exact reason why, but they don't let you pass in constructors, or they don't let you initialize variables with constructors like this inside of a class. So what you would have to do inside of a class when you're giving your objects a default value is you assign the object to an object, a temporary object created using this constructor with those variables passed into it. But we're going to get rid of all this because now we're finally back to where we need to be. Right here, we connect to this IP address, right? And this port. Very simple. And wait, actually, let me do something. Make sure none of my classes are starting soon. Regular bell schedule, bro. Man, if you guys, I don't know if high school AP Computer Science is supposed to be like this dumb easy, but it is dumb easy and simple. We were learning Scratch, and then we moved on to Python, and he's still on Python. We barely learned anything. We were just learning about lists or something. Like, bruh. All right, let's see. Starts 34, so I got 6 minutes. All right, let's take a look what we can do in those 6 minutes. So right here, we're going to connect to this asio endpoint object, and let's see what happens. Also, wait, one last thing I'm going to do is I'm just going to go to my previous code sample and copy this right here. We're going to say, if not error code, then print connected, and in any other circumstance, print failed to connect, and then print the error code.message. So what this does is error code just returns a Boolean value based on whether it has an error inside of it or whether it doesn't have any errors. So in this case, if it didn't have any errors, then this would be true. So we say the opposite of that. If it does have an error, then this is going to be true. Or, well, no. It returns true if it does have an error and false if it does not have an error. So what we're saying here is if it does have an error, then print connected. Or if it does not have an error, print connected. If it does have an error, print failed to connect. And then get the message function inside of the error code object and print that. The message function just is an asio internal function that just returns whatever error happened to the object. So right here, we're also going to put one more thing. System pause. For some reason, people really hate this function right here. All it does is I think it calls a command prompt function that just pauses your program. So we can see the final result of the program without it just finishing up and exiting out of nowhere. Right here, we're going to pause the system. Very nice and simply. This does not work on Linux, though, or anything like that. This only works on Windows, which is probably a big reason why people don't like it. But it's very easy for me to just use that to show what's going on. Let's run this now, and let's see what's going on. So we got nothing going on. It says failed to connect. No connection could be made because the target machine actively refused it. Well, that failed to connect is coming because we printed that out right here, and we said print error code.message. So right here, error code.message evidently contained no connection could be made because the target machine actively refused it. And that's just what asio is saying happened as an error in this case. And this press any key to continue is just our system pause right here. So we're going to continue and figure out why there was no connection. Well, if we think about it, what are we connecting to? We're connecting to 127.0.0.1, which is my computer, and my computer doesn't have anything going on at this port on 127.0.0.1. Nothing's going on over there. So in order to facilitate something going on, we're going to need to create a host application, right? So I'm going to say that this guy is going to be well, no, I'm not going to do it like that, actually. I'm going to do it more like, you got to check which ones of these will we always need. We'll always need all these objects over here. And so for this is when we're going to start branching out. We're going to say char mode equals nothing. I'm just going to copy a little bit of code that I created previously. And we're going to do this. And else, and we'll populate that later. So what's going on right here? Well, we're going to have a mode variable. I'm also going to have to go to my class soon. We're going to have a mode variable. We're going to print out join our host, and you're going to be able to put in J or H for your mode, and you're going to be able to say whether you're joining a server or hosting a server. And in this case, this mode is join mode because we're going to be trying to connect to an IP address. So right there, we'll put it on join mode. Okay. And then right here in this else statement, this would be if we do not put J, so our host mode is going to be down here. The reason I put the socket in here is because we're going to be creating sockets a little bit differently when we're hosting as opposed to joining, but we still can just use the same error code and IO and context devices right here that we created. So we're going to be evidently running two instances of this program. One of them is going to be hosting, and one of them is going to be joining. We can figure out what happens. Let's save this program, and I'm going to go to my class. So now we're going to have to create the host side of the application. So one man can host and one man can join the host right here. So in the host application, we're going to be connecting to the same IP address, I think. No, we don't even need an IP object right here. We're just going to create, in this case then, and I'm thinking about it, this IP really should not be in the int main, because we only really need that IP if we are connecting in join mode. Then we specify that that's the IP that we're connecting to, because if you're connecting in accept mode, you're just going to be accepting any requests that come your way, and you're going to be deciding what happens to those requests. So let's say we make an asio IP TCP acceptor object. So asio IP TCP acceptor object, and we're going to call this acceptor. And what this does is it accepts connections to the asio, your instance of your program. Now, what this requires you to pass into its constructor, you want to pass in an asio IO context right there, and we're going to pass in just the context that we created right here. Note that it's fine that we're going to be using this context for both joining and hosting, because in the join mode and the host mode, they're going to be in two separate applications. So we're going to be creating this IO context twice in two different instances of the program. So there's no issue that we're using the same IO context right here. Right here, it also needs another object. The acceptor needs an asio IP TCP endpoint object. So asio IP TCP endpoint object right here, and I'm going to have it has an empty constructor right now. It also, last thing, requires a port to connect to. So, oh wait, no, it does not require a port. The endpoint object requires a port. So this requires a context and an endpoint to connect to. This endpoint, if we remember correctly, it requires an asio IP address object, and instead of using up here, we use the make address function to get an asio IP address object. This time, we're just going to be specifying asio IP address object that is predefined, because we're not going to a specific address. We're not trying to accept a specific address. We're trying to accept any IPv4 address. And so the way that we specify we're trying to get any IPv4 address is we say asio IP TCP v4 and port. So this asio IP TCP v4 object right here, this function, returns a asio IP address object that signifies that we're trying to use any IPv4 address in this acceptor. And IPv4 address is just a regular IP address that has 4 numbers. So 1, 2, 3, 4. So whatever IPv4 address gets passed into the acceptor, it will accept. We also give it a port to listen on. So in this case, we're going to be listening on port 60,000 right here, because we created the port right there. Now that we have this acceptor object, we can just say acceptor.accept. Now that I'm realizing this socket actually should be down here, because we're only going to be using one socket. So we can say that we create a socket. And remember, we're going to be using a separate instance of the socket for the join mode and the host mode. So we can just accept this socket right here. And what this function will do is when this acceptor, the acceptor waits for a connection, or we create the acceptor object right here, and then this .accept function will wait for a connection, and then once it gets a connection, it'll place that connection into the socket, so we can start using the connection for stuff. So once the acceptor gets a connection, that's when this accept function will be finished. I don't know if it has a timeout. It might have a timeout of, I don't know, several minutes or seconds. I'm not sure. But we can just use the same socket object, because this socket object is not created using any type of IP address. It's only bound to the context right here. Down here, after we accept the socket, we're gonna do system pause because we want to be able to see what's going on. So let's run this. And now we get a mode. It says join or host. Well, actually, I'm going to close this for now. And I'm going to be going here and pressing open file directory. To find your exe files, you just go back one. And you go into this folder. You see your solution. And you go, in this case, I went debug mode in x86. So we're going to go into the debug folder. And it just has that right there. So I can run 2 instances of this now. If I press join on one, remember, this should not work. Failed to connect. No connection could be made because the target machine actively refused. On this one, I'm going to press host, though. Right? And it's asking for access to the firewall. Well, that's because this is asio trying to connect to the internet. So let's allow that right now. And now it's actively waiting for a connection. We can run this now. And we can say join. And this side immediately accepted the connection. This side checked, is the connection accepted? Yes, it was. So it says connected. So let's continue with that. We're not doing anything still. We're just connecting. So now how do we actually do something with this connection? So to do something with the connection, we're going to be using some functions. It's called read sum and write sum function. So in this join mode right here, we're going to need a buffer to be able to store our data. So right here, we're going to create a buffer, and we're going to call it, well, since we included array up here, come on, Joe Biden. Bro, I don't care about that. All right, so we're going to create std array object right here. And this array object is going to be an array of chars, because remember, buffers are chars because every single char represents 1 byte, since it is a size of 1 byte. And it's going to be a size of, I'm just going to say a kilobyte for now, 1024 bytes, because why not? That's going to be how large our buffer is. And I put ATD, which doesn't make much sense. We're going to do STD, which makes a little bit more sense. And we're going to call this read buff. And right here, we're going to say this read buff is not going to actually be initialized for now, right here. So read buff right there. Now, what we're going to do, we're going to call a socket.readSum function. And this readSum function, what it asks for is it asks for an asio buffer object. So we're going to put asio buffer, right? We want an asio buffer object. And this buffer object requires 2 things. This asio buffer object requires first somewhere to write all of the data into. And so in this case, this asio buffer object is nice. We don't have to put read buff dot data into it. We can just put read buff, because in this case, this buffer object just knows by default if you put in a standard library array, then it just writes into the standard library array. This is similar to the ifstream read function. Right? You're reading stuff and putting it into this read buff array. And right here, we're going to be saying as its second parameter, we're going to be saying as the second parameter that we want to specify the amount to read, or up to the amount to read. And since our read buff is of size 1024, we can put 1024, or we can put read buff dot size. This will just return an integer or a size type, something like that. that will specify how large the read buffer is. And so now this socket.readSum function is saying, all right, in the socket object that we created, the socket is connected to this endpoint. So read some data that's inside of the socket and put it into or use this asio buffer object to read the data into the read buffer that we just created up here, this array, and read up to a size equivalent to readBuffer.size. ReadBuffer.size will just return 1024 because that's the size of a read buffer. So we're at max reading 1024 characters or 1024 bytes. Okay, and then what we're going to do now is we're going to say, we're going to create a little for loop for char c in readBuff. Well, actually, we don't even need these because this is going to be a small function. std cout c. So what this should do is it should read a whole bunch of bytes or chars into the read buffer. And inside of the read buffer right here, what we're going to do is we're going to have this for loop to iterate through every single char inside of the read buffer and print them out onto the console. And then after that's finished, we're going to pause, system pause. So now let's run this and see what happens. To run this, well, we can run it like that, or since we're going to be running 2 instances, I'm going to go back here, then just click 2 instances like that. This file was overwritten with our new code because it just overwrites the file when you recompile it. So right here, we're going to press host. So now that guy's hosting, waiting for a connection. This guy is going to join, and now he provided the readSum function, which is not doing anything. Still not doing anything. It's still not doing anything. Okay, still not doing anything. And the reason for that is this readSum presumably does not have any data. And now we get an error because our program is bad. So something that's an issue is that we're using operating system sockets when we're doing this. And so the socket will not necessarily be destroyed when we exit the program. And so if there's data left into that socket, or if the program crashes, then data could be left into that socket. And so that's something that we have to keep mind of. Right now, we should not have put any data into that socket. So let's do that. Let's put some data into that socket. We're gonna have a variable right here called write, and this variable is gonna be let's call it just write, and it's gonna be actually a std string, if I can do this. And we're going to set it equal to Geobor. How's that? That looks quite nice. And we're going to use a new function called socket.writeSum. And it still requires an asio buffer object, but we need to pass in some stuff to write to this socket. So in this case, we're going to be writing to this socket a string. You can only really write arrays of chars or strings because this is expecting a whole bunch of characters that are 1 byte in size, and a string is very similar to an array of chars. In this asio buffer object, it just accepts a string into its buffer right here. So that's very useful. We can just say write. And what we can do is we can say write dot size, and this will return the size of the write object. I think also another thing you may be able to do, which would be quite nice, is if you just put write like this, it will infer how big write is, because write is a standard library string, and this asio buffer object may just have a constructor that by default figures out how big your string is and then writes it. I'm not sure if you can do that, for example, with an array right here. Let's check it. Do we even have to put read buffer.size? Because that would be saying that we're reading up to 1024 bytes. Can it just infer that if we just put read buffer? Yes, it does just infer that we're attempting to read exactly 1024 bytes, because that's the size of read buffer. I think in the case that, well, let's comment out this code and actually try. Control K C to comment, and we're gonna be having a char read buff, and we're going to be specifying that this read buff has a size of 1024, and that's it. So can it infer right here? It seems that it can infer that we're trying to read exactly the size of the read buffer. Let's check if this yells at us. No, it's not yelling at us. So it says that this function, it seems that this function can infer even for a regular array like this, that we're trying to read 1024 bytes. We're going to be using an array like this, though, a standard library array. And we're going to be passing that into read buffer, and it just infers that we're trying to read 1024 bytes. You can overwrite that if you don't want to read exactly 1024 bytes. You can read only the amount of bytes that you exactly want to read. Right here, though, we're writing the amount. We're writing just write to this. So our write variable is being written to this asio socket with the writesum function, and it's inferring the size of it is 6 bytes. So if we run this, what should happen is that the writesum function should write some data to the socket, and the readsum function should get back that data. So let's run this. This man's hosting now. This man is going to join, and we get some weird stuff on the screen, and it's very long as well. Well, we get Geobor, right? That was exactly what we sent. That's actually quite nice. And then we get a whole bunch of just garbage characters. And the reason for that is we're saying up here in the std cout for char c in read buffer, we're saying print out every single char no matter what the char is. We don't exactly know how much was read, and so we're printing out everything. And so initially we print out a whole bunch of good data that we just got from the writesum function right here. Then we're printing a whole bunch of bad data. Another issue is, how do we know that the writesum function has finished sending the data over? We can't be sure that it finished sending the data over. And so what happens if this readsum function is called before this writesum function gets to send over the data? Imagine this was a real world scenario where you don't know when the data is going to be written to the socket. And so when you call the readsum function, perhaps there will be no data there. You can build in delays, but we're going to figure out a way to do that a little bit later. Right. So what I should do now is I should show some methods to see how much data we read. I think if we do socket dot what is it? Socket dot I'm just looking at these. Socket dot. I'm not sure if this is exactly how much we need. It may be that we can actually just put that into the writesum function. let's see, this readSum function returns a size t. So, yeah, that's what I was looking for. So a size t is just a size in C++ that is commonly used. It's just a library size called size t, and that's presumably size type. And this is just some unsigned integer that's very large and can represent the size of pretty much any array that you need. And so it's commonly used inside of applications like this. We can say that we can either say size t bytes equals this. And so this socket.readSum function, it not only reads stuff into the read buffer, it will also return a value equivalent to how many bytes that it read into the read buffer, right here. And so we can have a size t object called bytes that is assigned to that right there. We can also say that this is not a size t object. We can say that this is an auto, because why not? If you're not exactly sure what the function returns, then you can put auto. But I'm going to put size t. And in this case, instead of using this whole array right here, what we're going to do is we're going to say for size t. No. We're just going to say nothing. We're going to say, wait, how's I going to do this? No. What I wanted to do is I actually wanted to do something like this. For size ti, I is less than bytes plus I. And then now what we're going to be doing is we're going to be printing out read buff I. Very simply, very easily, very nice. So what this should do is it should create a size ti, and we're going to be comparing it to bytes, which is also a size t, and we're going to be incrementing it and reading the contents of this read buff array based on the position of I. So if we run this again, there were build errors. So let's see what it says. Uninitialized local variable I used. Okay, this is because I has to equal 0. There we go. Now it works. So we're going to go back to this, run these programs once again, and we're going to see J for, or no, this guy wants to be H for host. This guy's going to join. Now connected, Geobor. Now it only prints up to the 6th character, because this for loop knows how many bytes were written because we have a size t bytes right here. Very nice. Another thing that we probably should do is we should say if socket, or well, this has to be in parentheses, is open. So this is open function returns true or false based on whether the socket is open, whether we can read and write stuff to it. So that's quite nice. And I'm just going to put this like this, even though Visual Studio is being weird. Like, why are you weird, bro? All right, there we go. Now we can read those bytes very nicely, and we check if the socket is open to make sure we're not getting any strange errors. Very simple right here. All right, after this, what we might want to do is we might want to write multiple stuff to the dude at the other side. So what we might say is instead of just writing Geobor, we might just have a string called write, and it equals nothing. And we're going to say while true, socket.writeSum, write, and we're going to say cin write. And we do not need like an end line or anything there. And this has to be an std cin. So right here, we get this cin function, or this while loop that will just constantly run, and it will write stuff into the write string right here. And then we're going to write that into the socket, and then this guy should read the socket. So let's see what happens. Compile it. If you're ever having issues with your program having like very strange errors that you really don't think should be going on, what I found to kind of help sometimes is pressing clean right here. And that's because when you compile a program, it does not always recompile the entire program. It tries to figure out, all right, what can I leave the same and what do I have to recompile based on the changes that he made. Sometimes it does not recompile stuff that it should have recompiled, and so you can clean it to force it to recompile everything from scratch and have the program exactly how it should be. Let's run this 2 times now though. Let's say host for this guy. Now this guy, I can't type in it yet because he's waiting for somebody to connect. I press join. Now this man is connected. Now I did type stuff into the cin because I typed stuff previously. But I can type something into the cin and I print it, and this guy gets it. But wait, look at that. And he didn't get it in a line, and also his program is already finished. Like, what if I write like that? His program is finished. So that's not very nice. What we should do here is we should also put this in a while loop. So while true, and do something like this. Now this while true loop will run forever until it hits a break, which we haven't really discussed. A break statement, I can actually just say it right very quickly. You can just put a break statement like that, and once the while loop hits a break statement, or a for loop, or any type of loop hits a break statement, then it just breaks the loop. No matter, even if the condition is true, it still just breaks the loop and it moves on to the next part of the program. So if you have a while true loop, the only way to break out of it is exit the program or have a break statement like that. Let's run this now. All right, something I also probably should do is I should say if socket is open, then I do all this stuff, and then I should say while true here. This is probably not as safe, because previously what we were doing, we were saying while true, check if the socket is open. If it's open, then read some data. Now what we're doing is we're checking if the socket is open once, and then we're just constantly reading some data. If it happens that the program crashes, then we're still gonna be trying to read data, and so that's not good. But for our purposes, this is fine. Because it only checks if this socket is open once, and if it is open, then it continuously reads data. Let's run this. Right here, we're gonna have one man hosting, one man is gonna be joining. He's connected. Now the guy who's hosting, I can type some stuff like DS. All right, this guy also gets that. This guy gets a little bit more, a little bit more, a little bit more, and a little bit more. I can write Geobor. He gets Geobor. Okay, quite nice. And now it crashes because it crashed because it tried to read some data that was not available or was not being sent or something along those lines. So that's why this probably should not be in a production application. So right here, though, what we're going to do is we're going to say that instead of pushing it into our array of chars right here, I'm going to comment this out. Control KC. We're just going to have a read buffer. Read buff. It's going to be an std string. Std string. And it's going to be of that size. Why am I putting those weird little things? All right, there we go. Read buff std string. Okay. Now over here, before we read into the read buff, imagine a scenario like this, right? This std string, this will probably read into it. It'll figure out how much it should read into the read buff string. Actually, I'm not sure if this will work, to be perfectly honest. I'm actually gonna go through it. So instead of doing this, I'm just gonna say this. First, let me test if this even works. So if we press host on this guy, this man is hosting now. This man is going to join. And he's constantly being printed something. Interesting. So this is constantly every single run of this loop. It is printing read buff, which is probably not ideal. So what we're going to be doing is we're going to be what is it called? How would I actually do this? I'm thinking. Well, we're going to say something like this. And print that. So if socket.readsum returns true, if you think about what does socket.readsum return, well, it returns a type size t, which is an unsigned integer. That means since it's an unsigned integer, if it's a 0, then it's going to be false. If it is a 1, then it's going to be true. So socket.readsum is going to be true if the amount of data that it reads is greater than 0 in this case. So let's run it now. And we're going to go into here. So this man is going to host. This man is going to join. So now this is not printing anything because it's only printing something if the amount of data is greater than 0. If we print Geobor, do they get data? No, why did they not get data? Read buffer. So apparently it's a little bit strange. Perhaps it could be that read buffer is not any size. So right here, this is what I'm going to do. I'm going to give it a size like that. And or it didn't have any default initialized value. And I press join. Now I press Geobor right here. Does this guy get Geobor? Still no. What if I do something like 2, 3, 4, 5, 6? So now this has 6 null characters. And if I'm if I am correct, then this should read this time around. No, it still does not read. Why is that? Read buff. Size. Let's run this once again. Let's do. Okay, let's go H for host, J for join. This guy's gonna type in Geobor, and he still does not get Geobor. That's a little bit strange. What if I just do greater than 0? Maybe it could be that the size t does not return any true or false value. Well, actually, now that I'm thinking about it, I think I'm just being dumb. Wait, let me try this one more time, and I'm pretty sure it's not going to work. This guy's going to type Geobor. Yep, and it doesn't work. Wait, no, maybe. Well, true. If socket dot available returns the amount of bytes that's available to the socket. So in this case, if it's greater than 0, then that means we have some bytes to read. And why did that do that? That should not have done that. Look, that's a perfectly good statement. I don't know why it was being weird. Oh, there is build errors. That's because I don't have that. So now let's check if this works. This guy's going to host, this guy's going to join, this guy is going to type Geobor, and now he starts printing. And he did not print anything. So, from what I understand, it does not look like... Oh, you know what it may be? Could it possibly be that this string is returning a const array of chars? That is very possible. It's very possible that the string is constant, and so it doesn't want to read. In that case, what we would have to do is just put a regular array, and we're going to be reading stuff. So right here, what I'm going to do is, if available is greater than 0, we're going to say bytes. Right here, I'm going to initialize bytes. Actually, I'm just going to initialize it at the top. So equals 0. Bytes equals that. And we're going to read bytes into the read buffer array. And then what we're going to do is we're going to somehow convert this array, I think, to a string. I'm not sure how I'm going to do that exactly yet. Well, the very crude and bad method, I think, would be do something like for size ti equals 0, I is less than bytes, and then last plus plus I. Then what we can do is we can say we can have a result std string iterator. I only wanted a string. Std string result equals nothing, and then we can say plus equals result plus equals read buffer 1 or read buffer I. So what this will do is it will go through every single character in I or every single character in the read buffer, and it'll add it to the result. Something I should do is I should say out here result equals empty string, just to reset the string before we do this operation right here. And then we're gonna, after we do that, we're gonna std cout result std end line like this. And now when we run this, we should be able to get host join. This man should be able to type Geobor, and this guy should get Geobor. Gamer, epic, and my online class is starting in a minute. Alright, so we got a little bit of time before AP Physics. Let's get this dub, gamers. What was I doing? Well, we have this result section. It pushes the bytes from the string into the result. Something I want to check. I'm not sure if this is possible to do. Instead of just saying result like that, I'm going to check if we can do something like this. So I'm going to use a new function, mem cpy, mem copy, and it requires a void pointer to the destination. So a void pointer is just a pointer that points to anything. It doesn't care. And you use void pointers just to deal with memory, usually as memory instead of like a specific object. This void pointer is going to point to our destination. And in this case, our destination is going to be result. I'm not sure that this is going to work. It might just crash my program. We'll see. We also need a source now, and the source has to be a void pointer to a source. And it's assuming that if this is like an array, then it's going to copy the entire array. So our source in this case is going to be read buffer dot data, because this wants a pointer and the dot data function returns a pointer. Result, we need to pass that in as a reference as well, I think. Actually, wait. I think we need to pass in result.data, because the result.data is similar to the array, or read buffer.data. It returns a pointer to the array that the string uses. And then we need to say how much do we want to copy over. In this case, we want to copy over probably bytes, because bytes is equivalent to how much we read. I'm pretty sure this will crash my program. Pretty sure I'm just going to get like a memory error. Assuming Windows. Okay, why did that take so long to compile? Whatever. Let's just go. Definitely going to work, guys. join, of course, connected. I'm going to type in Geobor. We get nothing. Oh, it did try to print something. I think I have a better way to do this. That would be if we wanted to make perhaps like an integer or something along those lines. Or would it? I'm not sure. Well, actually, wait. We passed in a string right here. So I'm thinking, why can't we copy the stuff into the string like that? And just maybe we can just pass in the reference to result. That actually may work. So this guy's going to host. This man's going to join. No, it did not work. And I don't know. I'm not exactly sure why, but it may be that strings are read only or something like that. They might be constant, which would make sense if that was the case. If they were constant, then it would make a lot of sense that that doesn't work. Some way that we could perhaps get this to a string, though, is we could include another header file. Look at that. I did that almost perfectly. I'm not sure if ssstream is bigger than fstream, but I tried to make it like even, like a staircase downwards. All right, but ssstream, it gives us access to a new string or stream object called a string stream, and it's decided whatever is put into this stream is turned into a string. So I'm gonna check, can we put that array of chars into the string stream? All right, so right here we're gonna have a std string stream object ss, and what we're gonna do, I'm gonna check just now, can, instead of using memcopy, can we take read buff and just push it into the string stream. Okay, so why did I do that? All right. It says there's no, you cannot push a standard library array. All right, let's try a pointer to an array of chars. You can push that into a string stream. All right, now, so I'm pushing this array of chars into the string stream, and then right here it's printing out result. What happens though if instead of printing out result, which is just a string, we completely get rid of result and instead just print ss.string. And what this does is it takes the contents of the string stream and returns a string based on whatever the contents of that stream is. So I'm not sure if this will work. It looks pretty promising to me. Let's host. Let's join. This man is going to type Geobor, and we get Geobor with a whole bunch of garbage. I see. We pushed the entire array into the string stream, which is not what we wanted to do. We wanted to push merely up to a certain amount of data. So it could be that we could use something like string stream dot, does it have a dot read function or something similar? Dot, because I want to read up to a certain amount of data. Yep, it does have a dot read function. You know, that's how I do my programming. I just look through the little list of functions that Visual Studio gives me. I pick one that looks promising. This read function, I don't know what it does, but I'm gonna assume it does pretty much the same thing as like the file streams. So it probably takes, if I were to guess, an array of chars. So to get that array of chars, we're just gonna do readBuff.data, and it probably takes a size. It does take a size. That's nice. So this size is going to be bytes, because remember, bytes is how much we read. So now I'm feeling pretty confident about this. So let's close this. This guy's going to host. This guy's going to join. And this man is going to type in Geobor. Oh, come on. That's a little bit disappointing, isn't it? Huh. Why did that not work? Well, ss.read. Okay, so here we are, back. I have figured out why it had not worked. And that's because I was using the read function. What we really want is the write function. So we have a string stream ss, and this is a stream object, you know, similar to a file stream or cout. And it has the .write function right here. So what we do initially is we use the socket.readSum function. Readsum and means that we're pushing the pushing data into the buffer that we provide for this function. We're providing the read buffer to this function, and so the data from the socket is being pushed in, or copied to that buffer. Right here, we're using the write function now to write the data from this buffer into the string stream. We were previously using the read function, and that did not work because using the read function would read data from the string stream into the buffer. But right here, we're using the write function to take data out of the buffer and put it into the string stream. Then right here, we're using a string stream function called str, and that just returns a string with whatever contents are inside of the string stream. Running this now. Let's change over to this mode. And let's press H to host, J to join, and let's type in Geobor. And see, look at that, perfect. We get Geobor. Gamer. But that is a little bit of an issue. Epic. Very, very interesting. So this stream evidently is not being cleared in any way. Now, something that we could try is that what if instead of using a string stream, remember there is remember file streams had if stream for in file stream and then of stream for out file stream. What if we used a o string stream for out string stream? Now let's run this once again. And let's go to debug mode. This guy's gonna host, this guy's gonna join, and this guy's gonna type, let's move this so we can see both, Geobor, gamer, and we still get Geobor gamer. Now, I'm not entirely sure if this will work, but when we were using the file streams, we could specify the mode that the file stream was in, right? Providing into the constructor the mode. And so this time we're gonna provide into this the mode. You can use, for example, you could use std o string stream and then provide the mode like out, for example. But I don't really think that's what we want. I don't know if that's what we want to do. No, actually, I think that is what we want to do. If we have it in out mode, I'm pretty sure this is actually going to be the same. But I was actually going to demonstrate something else. Not this. Well, I'm going to put H for this guy to host, J for this guy to join, and gamer, let's see, printed, Geobor, still just says gamer Geobor. And so just like with the file, when we used this outstream didn't clear itself. It didn't clear its contents. It didn't overwrite the contents. It just keeps appending it. It overwrites it initially, but then continues to append it, the contents. Something cool we can do though is imagine we don't even have this string stream. Control KC, and we don't even have this dot write function right here. Control KC. Remember that cout is also a stream. So what if we did cout dot write, and we provided inside of this right here read buffer dot data and bytes, because we're writing to the cout standard out stream. We're writing the contents of read buffer and the amount of bytes. And so now let's properly run this. This guy is going to host. This guy is going to join. This guy is going to type in Geobor, gamer, and look at that. It did not this time. Write any. It did not continue to append it. That's because we're writing it to the standard out stream. The standard out stream does not hold its data, clears its data generally after it puts it out. I'm not sure though. Could we perhaps, for example, I don't think we could do this, but I'm going to try this. And that's not yelling at me, so looks kind of good. I'm not sure if this is gonna work though, because for this to work, if you take a look at the code, that means that cout.write would have to return the out stream, and then we would push in this end line manipulator into that out stream. We'll see if that's the case. I honestly don't know if that's the case. And then J to join. This guy's gonna type in Geobor, and it says Geobor, gamer, and we get gamer. That does work. That's actually really quite nice. That's really quite useful. So this way we're using the standard out stream, and it's consistently just clearing itself instead of using any string streams. Now, something I wanted to ask about is, for example, what would what is the difference between the modes on a stream, like binary and regular mode? So if we specify that it's binary or we specify that it's regular, let's have this stream object backed. We're back ss.string. So this should print a string. I think what I might do though is I might attempt this. I'm not sure if this will work though. So we're just going to push the string stream into cout, and inside of the string stream I'm going to try to push end line. So I'm pushing a manipulator into the string stream right here, and let's not specify any mode for now. Let's check if this works. I'm not sure if this will work. So you can go back to debug. Geobor gamer, Geobor gamer. So evidently the end line manipulator did place a new line character, but it did not flush the string stream. I don't know exactly what the command for flushing a string stream would be, but I'm not really concerned with that right now. Might be just ss.ignore and then a certain amount of bytes to ignore, just like we used for CIN, not imbue. Something like that might be the proper syntax. Actually, it says that it has no member ignore. Well, let's check actually, because I'm a little bit curious right now. Clear? Clear would clear the flags though. Flush? I don't know. Maybe. I'm not exactly sure. So instead then, what we're going to do, I'm not going to be concerned with that right now. I'm just asking, what is the difference between putting like std o string stream binary. What's the difference between specifying that you're putting it in binary mode and what is the difference between not putting it in binary mode? Kind of showed the previous time that we were writing to files. I showed me putting it in binary mode, but what exactly was that? Something I also want to mention though is that all the different modes of most of the different standard library streams are really the same modes. So the binary mode of O-string stream is the same binary mode as I-string stream, or just string stream, or just F-stream, or even IF stream. And I think the most basic one is iOS, which is some type of input-output stream. And that's like the most basic namespace that you can use for it. So most people, I think, use iOS for Apple iOS binary. Okay. But what's the difference between putting binary mode and not binary mode? Well, let's check what happens when we put it in binary mode. Okay. Let's go to debug. This man is going to host. This man is going to join. Geobor. Okay. Gamer. Geobor gamer. Epic. The only 3 words I know. Geobor, gamer, and epic. Okay, that was what happened in binary mode. Now let's remove binary mode and let's see what happens. It's just going to be in default mode now. And we're going to use an H for host, a J for join. We're going to write here Geobor. Okay, we get Geobor gamer. We get Geobor gamer. Interesting. Epic. Get Geobor gamer epic. So it did the exact same thing. That's because, well, what is the difference between binary represented in C++ and a regular array of chars? Because if we put it in default mode, the stream is really looking for an array of chars. Well, if we put it in binary mode, the stream is really just looking for an array of chars. And that would kind of make the difference. It's platform dependent, depending on whether you're on Windows or Linux, but it just changes how it treats the new line character. Whenever it encounters a new line character, depending on whether you put it in binary mode or regular mode, it treats it somewhat differently. And so I think generally when you're putting when you're copying text, you usually want to use the text mode, and when you're copying other stuff that is not text, when you're copying just bytes, just use the binary mode. When you're, for example, copying a text file, use the default mode. When you're copying any other type of file, use the regular mode. Something I also wanted to mention is for an application like this, trying to use this application over the actual internet, like, well, imagine you have two computers in your house and you set it so the IP address, or so this program connects to a different computer in your own home network's IP address. You won't have any issues there. This program will run fine and send the data to that IP address if it accepts. But sending it to an outside IP address, somebody else's IP address, if you give your friend a copy of this program and you have this program on your computer, he types in your IP address and tries to run it, it most likely will not work. And the reason for that is probably because the connection would be blocked through the Windows firewall. And if not blocked through the Windows firewall, then it could be that it's the ports that you're using are blocked, whether it be that your internet service provider blocked those ports or you need to port forward them. I'm not exactly sure whether you would need to port forward them or not. But using this in a real world scenario, most likely you would have to set a firewall flag inside of your Windows settings or just disable the firewall to get it to transfer data. And instead of, you would have to just provide your friend's actual IP address as the server that you're connecting to, because that's just how internet connections work. You can't, you would need his actual IP address. All right, let's think of some other things to do though. Well, I think that what I may do, oh, well, here's a good thing. How do you send numbers over the internet? We know how to send text, but how do you send numbers over the internet? Well, right here, we're sending over a string, which just goes into this buffer, very simply. And if we check what this buffer wants an array of chars. So it pretty much only accepts arrays of chars. So instead of well, actually we're still gonna have write as our variable name, but this time we're gonna have an integer, int write, and we're gonna push from cin into write. And now how do you send write over the internet? Well, first you need to convert write to an array of chars. And the way that you would do that is you would say, well, what is write? Write is a 32-bit integer, and each char is 8 bits. That means that you would need 4 bytes, and you would need an array of chars that is a size of 4 bytes. So we're going to do std array, have a char, and it's going to be 4 bytes. And this will allow you to send your send exactly one 32-bit chunk of data. So 32 bits, 4 bytes. And we have this int write over here. I'm going to put this actually higher up. Well, maybe I should do this super expert method. Control X. Ooh, look at that. Look how fancy I am now. Control V. Yeah, that's how fancy I am that I can't even get it correct. All right. Let's check if I can use keyboard shortcuts to jump around. No. Okay, interesting. That was a struggle. Let's paste that in here though. Okay, now we have an integer right. We have a right buffer, and we're gonna what we need to do, we're pushing from cin into that right. So how do we get that right into the right buffer so that we can send it? Well, you can use this function, which I tried to use previously, memcopy, and this requires a void pointer as its destination. So what is the destination going to be? Well, it's going to be right buff dot data, right? Because that's an array that it's a pointer to an array that we can drop all the data at, and we're going to need a something to send. So what can we send? Well, let's send right, and it's yelling at us because it expects a pointer to right, and so you can just put a reference right here, because a reference is kind of almost acts like a pointer literal. And then last, we need a size t to send, and so we know the size, so I'm just going to put 4. You could also do something like size of int. I don't know if that works. Or you could do size of right. All right, now we're gonna have to push the right buffer through here, or right buff. And since the right buff is a standard library array, and this writesum function understands, or this asio buffer object understands standard library arrays, this is all good and nice. So now we're going to be writing, we should at least be writing integers to the person that's joining this IP address. In this case though, what I'm going to do is I'm going to get rid of all this string stream stuff, and I'm just going to be doing how do you get those integers on the other side? How do you convert them back into an integer? Well, on this side we're going to need an integer to convert it back into. So in this case our integer is going to be an int read. We're just going to set that equal to 0, I guess. And we can set this also equal to 0. Let's get rid of the string stream. And so now we have an integer read. This integer read is going to be copied and pasted. Oh, dang. I thought that would look cool. I thought I would be able to do that nicely, but no. All right, there we go. Now it looks a little bit nicer, right? This line's the shortest, then longer, then, oh, never mind. This IP address is shorter, whatever. I don't care. Okay, so we have this integer read, and what we know is that right here, we're reading in this buffer we're going to be reading an amount equivalent to even though that this buffer is 1024 bytes, we're only going to be reading 4 bytes, right? So what we can do is we can say something like memcopy, and remember memcopy wants a pointer that's the destination of the destination of where we copy the memory, where we copy the bits and bytes. So we're going to be copying those bytes into read, because read is an integer. It's going to treat read actually kind of like an array, but if you don't know how arrays act, arrays and integers act the same. If there's an array of size 4 bytes, it's the same almost the same as an integer of size 4 bytes. Going to the next, if you're at a pointer to the first element in an integer, the first byte in an integer, and you're have an array that has the exact same byte arrangement. So imagine we have a integer that looks like, that's 1, 2, 3, 4, 5, 6, 7, 8. And this, just to make it simple, if we have an integer that looks like this in terms of bytes, we could also have an array that looks exactly the same. We could have copied just the memory from the array, and this bottom section might be an array of chars. So this is 4 different chars in the exact same arrangement as this one integer. So we could just copy the memory from this array of chars to this integer, and this integer could almost act like an array, because when we're iterating through an array, we're really kind of saying start at the first object, and when we want to go to the next object, well, we find the pointer to the first object, add 1 to that pointer, and that's the second object. If we treated this integer kind of like an array, we would say that this first 8 bits is the first object of that integer, and we could iterate through it kind of like an array. But we're just copying the data over right here. So we're copying the data to read as if read was a array of chars almost. And we need a source for this. And what we can use for the source is we can use read buff.data. And then we can say that how much do we want to transfer? Well, bytes, because bytes is going to equal how much that we read, and we're going to read in this case 4 bytes each time. Something that we might have to be careful of is if somehow this read function is able to read more than 4 bytes, we're going to be trying to copy greater than 4 bytes into an integer which only holds 4 bytes, and that would crash probably. So we have to, if we could only do something like this if we're sure that this readsum function is only ever going to be reading a maximum of 4 bytes. You could also say though that instead of saying that you can read up to the buffer.size, you could either lower the buffer to be only 4 bytes and read 1 integer at a time, which might be inefficient, or you could do a whole bunch of different types of stuff, like you could keep the buffer the same size but only say that we're allowed to read up to a maximum of 4 bytes right here. Or you could, for example, read a whole bunch of integers to the read buffer and then parse through those integers later. But right here, we're just going to be doing this simply like this. We're going to copy the bytes from the read buffer into our read integer, and we're going to copy an amount of bytes equivalent to bytes, which is a size t that signifies how much we read. And last thing we're going to do is std cout read, and in this case read should be an integer. And if you didn't know, well, cout should pretty much just take the contents of the integer, push it into the stream, and then print it out as a char onto the console. So we'll see that happen. So I'm going to type in H for this guy to host, J for this guy to join. This guy is going to type in 1, and we get a 1. I type in 2, we get a 2, and 3, and 4, and 5. And how is this different from just what we did previously? Well, it's different now because we're getting actual integer data types. So read right here is an actual integer. It's not a string that represents an integer. It's a full, real integer. And so if you're perhaps making a game and your game requires you to send integers over the internet, you would most likely have to do something similar to this type of method. And you would have to have perhaps a different thread that sends these integers every amount of ticks. So 60 ticks a second, perhaps. And since these are integers, we can write up to about 2 billion. So if we write 200, it's going to work. We get an integer of 200. Now if we do 3 billion, which is 3 with 9 zeros, I think, it starts breaking. Yep. I don't know what kind of error that was, but you see, we entered an integer that was larger than the maximum allowed size. So it wasn't being very happy about that. Yeah, that's how you would pretty much send integers and stuff over the internet. So next lesson, I think we're gonna do basic threading and basic locks. And I think that'll be the end of this tutorial then. I lied. We're just gonna be doing a little demonstration of how you would send text over the internet and then write that text to a file. Like, pretty simple stuff. That's why we have fstream, of course. We don't really need string stream, now that I think about it. We really can. We don't need this memcopy either, because we're not copying integers to files. We're copying bytes to files. So right here, let's get rid of that. We don't need this write buffer either, because we're just going to be writing strings. Finally, school is over for me though. Easy claps, gamers. Alright, so cin write, and we're going to write stuff to write. Yeah, we're going to write stuff to the socket, and we're going to input that from right over here. And after we do that, all we got to do is we got to create over here, well, our integer read. I'm going to change this into being a ofstream std ofstream. And we're going to call this w file. And we're going to construct this using a path just called output.cpp and put that in quotes. Okay, it's being weird. There we go. Output.cpp in quotes. And then after this in quotes, what we're going to put is we're going to put the mode. So this is going to be std iOS append, I guess. Or I'm just going to have this in out mode, I guess. Actually, I'm going to put the OR operator, and we're going to have std or std iOS. Actually, you know, we're not even going to put it in binary mode. There's not much of a reason to. Alright, now we do this. Now we're in ofstream file, or object right there. And we're reading stuff into the buffer right over there. Now we very simply should be able to take in this w file, call write on it, provide in the buffer. So in this case, the buffer that we're going to be writing is just going to be read buff dot data, because this wants a pointer to an array of chars. Then what is the size that we're going to be writing to the file? Well, it's going to be bytes right there. And this, we can just do that. So there we go, easy claps. This should just create a file allowing us to write stuff, or create a program that allows us to write stuff to files. Right here is going to be debug mode. I'm also going to open a folder right here just so we can see, does it print stuff to output, or does it make an output folder? I got too many windows up in here. Okay, here we go. Now we can see host, join, connected. This host is going to type Geobor. Press enter. Did that work? Right here, output.cpp. Is there anything inside of it? Nothing inside of it for some reason. Gamer. It's actually a little bit strange. Why is there nothing inside of that file? Oh, now there is. After we closed those programs, it updated it. So I don't know why exactly that is the case. Maybe a quirk of how Windows works, but it looks like to me that this output.cpp only changed after we closed these for some reason, and it's a little bit strange, but whatever. We're gonna do this is overwritten, as you can see now. It's 0 kilobytes. It says Geobor gamer epic. Then close this. Now it says Geobor gamer epic right there in that CPP file. So that's a very simple tutorial on how to do that. I don't know exactly how the file writing mechanics works in Windows. Like, I don't know where the data is placed after this write function. Is it placed in temporary directory? Is it placed in memory? I have no clue. That'd be something useful for me to look up, because evidently what happened was that even after writing the data, if I pressed H right here and J right here, and I wrote Geobor, for some reason this output.cpp file does not have Geobor inside of it. So I don't know where that Geobor is currently. I don't know if it's in some temporary directory or in memory, or how to get it, or how to push it to the actual file. It may be that this file needs to be closed before you can check the contents. So I'm actually going to test that, because I feel like that would be useful to know. It seems like that might be true, because the stream object should be destroyed after the program is closed, and it looks like after the program is closed is when then the data actually gets written to the file or something like that. So instead of actually constructing the stream object right here, we're gonna just construct it with no mode, just like this. And then right here, when we're writing the file, we're gonna say w file.open, and we're gonna give it the path. So output.cpp. Gonna check if this is what we need to do. And then w file.close That's it. So this is gonna open this path, and this is gonna destroy the object. So this should be fine. Let's go to debug right here. And we're gonna go, this guy's gonna host, this guy's gonna join, this guy's gonna type Geobor. My guess is, yep, this does have Geobor in it. I don't know exactly why that happens the way it does. Is it that you cannot read a file while it is open in this program? Because if you've ever tried something like, if you've ever tried deleting a file before, actually, I'll demonstrate this. So I'm just going to Ctrl Z this to where it was back before. Bro, what is this? Career. What is this? If you are still interested in Orleans Technical College, I don't even know what that is, bro. I never did anything with New Orleans Technical College. What? Bro, I'm not even gonna go to college for real. Bro, I can just sit in my room and watch anime for the rest of my life. Easy dubs. Alright. So, right here, we are writing this file. And this, when you call this constructor right here, this object is not deleted until it goes out of scope. And it would go out of scope either when a function finishes, for example, or when the program finishes, because when the program finishes, that goes out of scope and the objects all get destroyed. Let's run this once again. I want to show what I was demonstrating. What I was trying to demonstrate. I'm pretty confident in what I'm gonna show. So I'm pretty sure if I press H right here to host and J right here to join, and I press gamer right here, it creates this output.cpp file. What if I try to delete it right now? This action can't be completed because it's open in network tutorial.exe. If you've ever seen this error in Windows that the file is open in another program, this is that error right now. It's open in that program right now. It is not out of scope, and so the stream is still open, and so it does not let you delete the file, which is, you know, as you would expect. So evidently, even after it writes, though the stream writes, it still is open somewhere. What I want to check is inside of Visual Studio, we should actually be able to check how much memory our program is taking up. So, for example, what I'm going to do is I'm going to launch this guy in Visual Studio, and now it's in debug mode. So we can see the exact amount of memory that we are holding, which is exactly 996 kilobytes. And I'm going to run a separate instance of this program. This one's not in debug mode. Or, well, this one's not in Visual Studio. I press H, right, and this guy's hosting now. And this guy is still using just 996 kilobytes. I press J to join, and the amount of kilobytes went up to 1,020. Okay, now what happens if I press Geobor? Does the amount of kilobytes go up? It's now at 1 megabyte, it says. I say gamer. I'm not seeing it go up. I just want to type a whole bunch to see, does this go up? I don't know why it went down right there. Now it's at 892 kilobytes. What I'm seeing right now is, even though the file is open in the program, or at least it should be open in the program. Is that correct? The file should be open in the program. Oh, it is open in the program. If we go to network tutorial, I'm running the program from Visual Studio this time, so it's going to be in this folder, output.cpp. Even though it's open in the program, it seems that Windows is writing all of this not to memory. Because if it was writing all of this to memory, then I would assume that the memory that the program is using would be going up. But I don't see that. I type in all these G's, it should be writing it to the file. But it looks like that is not held in memory anywhere. I don't know, maybe it's held in some type of temporary directory and waits till the program finishes to write that to the actual file. That seems most likely to me, which is quite interesting. But it's only when this program is, when this thing is destroyed right here, when the stream object is destroyed, you're going to watch this 0 kilobytes. Right here, it's going to change to 1 kilobytes because the stream object is going to be destroyed, and then everything's going to be written to the file. Now it says 1 kilobyte. Well, actually, now that I'm thinking about it, it very well could be that I just wasn't seeing the amount of data increase in Visual Studio because it was just too small of an amount of data. So I kind of am interested in this, so I'm just going to run it again. This guy is evidently going to host because we want the guy who's writing the files to test it. So currently we are at a cool 1 megabyte. Type in a whole bunch of G's. We went up a tiny bit right here. We're at slightly lower than 1 megabyte. Now we went up to, or well, we were slightly lower and we went up a certain amount. I don't know if this 1 megabyte is going to drop down like it was last time. I'm just going to, can I press? So I should be able to write a single kilobyte, I think. I think I'm capable of doing that. So we're at 892 kilobytes. So I'm just going to keep writing G's until I think that it probably increased a kilobyte. And let's check if it goes to 893. No, it's still at 892. Yeah, it seems like this is stored somewhere in some temporary directory or something. Because if this was stored in memory, then I would expect the amount of memory that the program is using to go up. Still 892. Yeah, that's interesting. That's nice to know, though, that while we're writing stuff to files, we don't have to worry about the amount of kilobytes or the amount of memory that the stream is using taking up memory, or the amount of space that the stream is using taking up memory. We don't have to worry about that, it doesn't seem like. So what else are we going to do? I guess let's very quickly go over bitsets. Bitsets are kind of useful. Let's check if bitset, and I'm gonna copy this, move it down, because look, that looks a little bit nicer. Okay, so a bitset is a object that just represents data, so like zeros and ones. So to get a bitset, we can very simply do something like this, which is what I'm actually, let me get rid of all these files because we're not writing to files anymore, and get rid of this OF stream object, This time, all we're going to do is we're going to initialize a bitset object, or well, we're going to loop through all of the chars inside of the array. So for char C, inside of read buffer, we don't even really need these angled brackets or curly brackets. We can say std, or no, we do need those because I'm going to try to initialize a bit set. Okay, so we got to say std bit set x, and this we pass into its constructor the thing that we want to create a bit set out of. So in this case, we're going to create a bit set out of this char. I think this it does not accept arrays, I know, but it does, and it does not accept pointers. Well, it does accept pointers, but it gives you the bit representation of the pointer, not the object underlying the pointer. So also, we have to specify how many bits, not bytes this time. This is bits that this bit set is going to hold. And a char is 8 bits, so we're going to say 8. We're going to say, I'm going to pass in C here. And we're going to say, so all this is doing is we have a bit set with a size of 8 bits, and we're constructing it from our char C. And this takes up to a 64-bit long, I'm pretty sure, as its maximum amount of bits that it can represent. There is methods to add on greater than 64 bits, but it's a little bit wordy. In this case, we're just going to be reinitializing the variable for every single char inside of the read buffer. Actually, I think that would even be a little bit wordy. So I'm just going to say, instead of char C, or it would give us too much data, because I'll do it for all 1024 bytes. In this case, all I want to do it for is int or size t I equals 0. I is less than bytes and plus I. Then I can just do C, or well, no, I can do read buff I right here. I can construct it using read buff I, which is going to return us that char. And we're going to print out the bit set every single time it's constructed. Actually, another way we could, well, let's do this for now. That's already compiled. Let's just go to debug right here. So I'm going to press H to host with this guy, J to join with this guy, and we're going to say Geobor. And this gives us the bit representation of every single character in Geobor. So you can see that is 6 different chars, and it gives us the bit representation. So if we print a G, you're going to see it gives us the char representation of a G. If we press a H, it gives us the char representation of an H every single time. If we press a K, it gives us a K. If we press a 1, it gives us a 1. If we press a 0, it gives us a 0. I think, does /0 give a null character? No, it does not. It gives us 2 separate characters. It's thinking that we're typing into syn 2 different times, / and then a 0. So we're typing in 2 different chars into syn. So it prints 2 different values. And I think maybe if I put nothing, no, it didn't do anything. I thought if I put nothing, it might pass in a null character into there. And this would be all zeros if that was a null character. But yeah, that's really quickly. If you want to check what the underlying bytes of something is, you can use a bit set. And it takes only usually kind of just integral types. It doesn't take arrays. It has issues with arrays, but you can do what I did right here to return the values inside of arrays for your bit sets. All right, something that I want to try is, what is this? Expected a declaration. If else. If while is that, wait, is that this? Yeah, there we go. So how can we check what types of sockets that we're accepting? Well, if we print, if we just do std cout socket dot get, no, so I think remote endpoint. And we put, this is a function that just is included within a socket. This will give us the remote endpoint of whatever we are, whatever is our socket connected to. We can also do, I think something like, actually let me look through here because I don't remember exactly what the function is called. There's a lot of functions. Local endpoint. Well, I should have known that. That seems pretty easy. I thought it might have just been called endpoint with nothing else. But now on the host side, we're going to be able to print the local and remote endpoints. I'm also going to do that right here. Well, actually, I'm going to put that inside the if socket is open function, or if socket is open, little declaration. Now let's compile this. Let's go over to our little, well, actually, let's close some of these like that. Let's press H to host here, J to go here, and we'll see what is going on. Well, okay, this guy's hosting, so he's saying print remote endpoint. Well, it says 127.0.0.1. Yeah, that's this machine. 52,161. That means that that is communicating, or we are communicating to that on a port of 161. If we check, so this means that the remote endpoint we're communicating is on a port of 52,600 or 161. Well, how is that possible? We're putting in right here a port for it. Well, actually, the way that this works is when you connect to a socket, when you're connecting to a socket, you're saying right here that on this socket.connect, you're saying that you want to connect to this port on the other guy's machine. So socket.connect, when you're giving it an endpoint object, you're connecting to that port on the other guy's machine. So if we had two machines, let's pull out the notepad for this. If we had 10.0.1.4 and 10.0.1.15, if this guy is hosting something on port 60,000, then when you create an endpoint on this guy to connect to 10.0.1.4, you are going to be connecting to 10.0.1.4 port 60,000. And you're going to be connecting to that guy. When you create an endpoint to connect to a server, you're specifying that you want to connect to that port on that server. When you connect to that server, though, the server is going to need a port to talk back to you on. So it automatically creates a port for 10.0.1.4 to talk back to you at some random port. So in this case, it was like 52,601 or something like that. So it automatically creates a port for you to connect to. This is the server right here, the 10.0.1.4. And when you try to connect to the 10.0.1.4 at port 60,000, you're going to need a port to talk to them on. And so 10.0.1.4 will see you trying to connect on 60,000, and it will connect to you on whatever randomly generated port that you got. So in this case, it's going to be 52,601. It's just going to be a free port that nobody uses. And down here, when we're specifying on this acceptor object, we're saying that when we specify port right here, we're not connecting to a endpoint at that port. We're accepting sockets that try to connect to us on that port right here. So this server is communicating on port 60,000 right here. It's predetermined, and it's accepting connections on port 60,000. When you call the socket.connect, you try to connect to port 60,000 on whatever other server that you're getting, and it just gives you some random address for the server to talk back to you at, because you need a port that's open for the server to communicate back to you with, and asio automatically creates that for you, or maybe the operating system, I'm not sure which one, but you automatically get that port, which is quite nice. Now, what you could use this function for, as you can see, this function could be used for example checking, do we want to connect to this IP address? If we get a connection, we could, instead of reading something from the connection, ask the user, do you want to connect to this IP address? And if you press yes, then connect or accept the connection. Or if you press yes, then you can start reading stuff. If you press no, then do not read anything, because imagine somebody connects to your server. What happens if they send some malicious data to your server and you start reading that data? Well, you know, I don't know exactly what's going to happen, but they probably don't have good intentions. And when you're opening these ports and you're hosting these servers, you're opening your computer for other people to start sending you stuff. And so, especially if you have your firewall unblocked and such. But that means when you're reading the data from these sockets, you might want to deliberately accept a socket. And so you could, for example, have a system that prints out this the IP that you just accepted the connection to, and then ask, do you want to start reading data from this? And if you say no, then you can close the connection and try to open a new socket. And we'll demonstrate that after I go grab something to eat. So let's try to implement accepting a socket. So the way that we're going to do that is we're going to say if well, actually, how are we going to do this? We're going to say, well, std cout well, actually, we're already using std cout. Do want or I'm just gonna have this like this. Do you want to accept and then I gotta have on this side well no, I think I'm gonna do it like this. Nope, like and if we run this, do you want to accept that? And then I can specify, yep, and then it's going to continue. And then I can just put an if statement right here to say, alright, well, I need a, or bool, or no, char accept equals, accept is going to equal, in this case, /0, because we want it to be a null character. Why is that yelling at me? Oh, it's because it's in double quotes. There we go. So it says, do you want to accept that? Then I'm going to say if accept equals then use this loop right here. And that's it. Or well, actually, I'm going to put as the else statement. What am I doing? Socket dot shut down matches argument list. Socket down both. I don't know what actually. Oh snap! I didn't know that. That's how you access enums. That's strange. Why can't I access the shutdown both enum from the scope operator? I don't know why. Actually, let me take a look real quick where this is at. So enum shutdown type, and it's in the class socket base. I'm not sure why you have to access this enum right here with the dot operator instead of the scope operator. I thought you normally have to use the scope operator to access enums, but you haven't learned what enums are yet. All you have to know about these enums, these mythical enum objects I'm talking about, is that this socket.shutdownBoth is used to specify a mode for this shutdown function. And I looked on the asio documentation. They just said that before using the socket.close function, you should probably use the socket.shutdown function. So I'm just going to do socket.close now. So the shutdown function, what it does is it's supposed to stop reading and writing from the socket. So this shutdown both means that you're stopping both reading and writing. You can also do stop receive or socket.receive, something like that. But I'm just going to do socket dot socket dot, what's it called? Shut down both. And then this close function, what this does is it closes down the system socket within Windows. So Windows has a socket object that it uses to pass data between the network, and asio uses those sockets. So you need this close function to close that system socket. Normally this system socket is closed not when you go out of scope. When you go out of scope in the program, the socket will not be closed, because just like when we use the fstream.open function, that object will persist even after you go out of scope. So right here we use the socket.connect function right here. This connects the socket to whatever this is, and even if this whole function finishes and you go back into another function, imagine this was not int main, this was another function, you called it and you use socket.connect, and then you went back to your original int main function, this socket would not be destroyed. It would be sitting in your memory somewhere. And that's why you have to call socket.close on sockets if you want to close them. If you exit your program, the socket should be automatically closed. And also, if your program crashes, then the sockets will not be closed until Windows takes care of them in 10 minutes or something like that. So those, you have to make sure they're closed. Then by the nature of these sockets, they could have some type of data inside of them even before you open your program. You could open your program, try to connect to this socket, and it already has a system socket open with some data in it. And so when you try to read your program data, you could start reading garbage data because there was already a socket open with all that data inside of it. And so we're probably going to implement another function to clean out to make sure when we connect to the socket for the first time, to clean out all of the data from it and then get it ready for using this program. So we're going to use the socket.shutdown function, the socket.close function. This will close the system socket so we won't have any memory leaks. And so the socket doesn't have any leftover data inside of it. And that's it. We could also do something along the lines of this, if I'm correct. While true, and you could put these all like that. You could go like this, and that was not a good idea. Let's do that and then tab all of this again. So now this is going to continuously accept the socket and then perform these operations to check if you want to accept the socket. And if you want to accept the socket, then it'll do all this stuff right here. What we should mention is that how do you get out of this while loop? Well, the way I'm going to get out of this while loop is I'm just going to say on the socket.close function, well, actually, no, I'm not going to say that. This while loop, we're just going to get out of it when we close the program, pretty much. So the way that this while loop works is we're going to constantly accept the socket, and then we're going to check, do you want to accept the connection? Do you want to start reading from the socket, or writing to the socket and reading from the socket? If yes, then you can start writing to the socket right here. And if no, then we're going to shut down the socket, close the system socket, and then accept the socket once again. And system pause here too for when the program is finished. Right here, we're going to be implementing something similar. We're going to say if socket is open, we're going to say while socket dot available is greater than while socket.available is greater than 0, what we're going to do is we're going to push that all into our read buffer and then just clear it just to read everything. And we're not going to use that data for anything. So this is to make sure that there's nothing in the socket before we start reading the actual data. In this case, I'm going to say socket.readSum and read that into the read buffer. And that's really kind of it. That's all we really have to do. And then right here is when we're actually reading. So we clean out the socket right here, then we get primed for the actual reading. Right here, what I'm going to do is I'm going to say IP no longer equals 127.0.0.1. We're going to say IP in this case actually only equals, well, we're going to say std cout enter an IP address. Well, actually, I'm not going to have that. This is just going to be ended like that. Then we're going to cin IP and this is too far back or too far forward. This actually should be closer to right here. Now if we run this, we should have some other stuff implemented. So this guy's going to host, this guy's going to join, enter an IP address. Well, we're going to do 10.0.1.4. Do you want to accept 10.0.1.4? 52,305. Well, let's say yes. That's a little bit strange. Actually, I have not much of a clue of why that's going on. Oh, I did not see an accept right here. So and we need to see in that accept to make sure our mode is correct for this section. So right here. And if you were an actual good coder, your code would look a lot better than mine and not everything would just be in the console like this. But we're going to enter an IP address 10.0.1.4 because that's my local IP address. Do you want to connect to 10.0.1.4? Yes. And now I can start writing stuff. I have not much of an idea of why that didn't send. Let's close this file and then reopen it so we can see what do the actual colors look like. Okay, so if that equals that, then socket.writeSum was this not reading sum? If socket is open while read sum is greater than 0, while socket.available is greater than 0, do that. But this should only run once. Is this running all the time? What I'm going to do is I'm also going to see out something here as a debugging. So std see out Geobor to check if this is doing stuff. Because it would make sense if we're not able to read anything. Oh, no, I see why we weren't able to read anything. No, this function worked perfectly fine. The real reason we weren't able to read anything is because we weren't printing it out right here. We can just do std see out. Okay. Let's try that again. Okay, we don't even need that. I remember it's dot write. All right. Read buff dot data. Easy claps. Speed run. Okay. Size t bytes. There we go. That was the slowest line of code ever written. All right. Now we should be able to do this. All right. So I'm going to say H for host. This is going to join 10.0.1.4 connected. Yes, I do want to accept that IP address. Now I can type Geobor and we get Geobor. Gamer types gamer. Epic types epic. Easy claps. One thing I want to check is, let's check what happens if we do not accept the connection now. So if we press H and J at 10.0.1.4, right, it says connected. Do you want to accept the connection? No. So what should have happened right here? Else socket.shutdown, socket.closed, then it should accept another connection. So right now, this right here is waiting to accept another connection. So something that I could do to make that more clear is I could do std see out waiting for connection dot dot dot. There we go. Let's run this now. And we're going to go into here. We're going to say this guy's going to host. So it's waiting for a connection. This guy's going to join. 10.0.1.4. Do you want to accept that? No. Now it's waiting for another connection. So if we exit this guy and then run him again, press J to join, 0.1.4. Do you want to accept that? This time, yes. Now, this connected right here is a little bit misleading. It's not telling us whether the server accepted our connection. It's just saying, it's more so saying that we found a connection at that server. And so I think a better descriptor, instead of connected, we could say is found connection at, and then put in the remote endpoint. So we could say right here, found at this connection is going to be something like socket dot remote endpoint, and this returns the remote endpoint of what we're trying to connect to. So now when we connect. Even if he presses no, we're not going to say that we're connected. We're just saying that we found a connection there. And then we can do a further check to make sure that the server actually accepted the connection. So this guy's going to host. It's waiting for a connection. Press J to join. 10.0.1.4. Found connection at 10.0.1.4. 60,000. Do you want to accept this? Yes. We did not implement anything for that far past though. I can always just put something like that. Geobor, and now we'll get Geobor. So now we're going to implement a check to make sure that when this man presses Y to accept the connection, the client gets notified that the connection was accepted. So if accept equals Y, what we're going to do is we're going to write something to the socket real quick to notify the other server, or to notify the other client. So we're going to write, instead of the write variable, we're just going to write, I think in this case, we want to write a Y. Is that possible? Will it allow us to do that? No, it does not want to allow us to write a char Y. That kind of would make sense. And you can't say like a reference to Y or anything like that. That's actually something I never thought about. How would you put in a pointer as like a literal? You kind of would just need a reference to something. Well, actually, what we can say is that we have a const char reference. It's called why am I even trying to do that? There's not much of a point. We're just going to say char. Well, actually, now that I think about it, we can just send accept to them, now that I think about it, because accept would equal Y anyway. So we're going to write accept to them. And accept is a char. It's a regular char. So we're going to pass in accept as a reference, because that's going to give it a pointer. Now that's a char pointer. We're going to say that it's a size of 1, and now it's happy. There we go. So we're going to send a 1 byte, which is a char pointer accept. Very simple. And in any other case, we're going to also just write accept to the, well, actually, now that I think about it, we can just write accept right here. We don't even have to do this check, because we're going to be writing accept to them either way. We're going to be writing accept to them whether we did not accept it or whether we did accept it. And that's safe as long as we're not reading anything from them. Because if we accept the connection, even if we don't accept the connection, we can still write stuff to them without getting any malicious data back. We just have to make sure not to read anything from them if we're not accepting the connection. If we're accepting the connection, then we can also write some data to them and read some data back from them, because we, since we accepted the connection, we're accepting that we trust this person that's connecting. So we're going to write accept to them, and then on their side, the client side, they're going to check whether accept is there. So they're going to check what is the value of accept. So we're going to write to their buffer. They're just going to do a very quick socket.readSum right here.
1.2 billion.
And in this socket.readSum, they're going to read it into the read buffer. And they're going to read up to read buffer.size. Then we're going to say, actually right here. Actually, no. I think like this would be nicer. If read buff 0 equals y. And that's because since we're reading, initially here, what we're doing is we're clearing the socket. Then we're going to read, check whether he accepted the connection, the server accepted the connection or not. Right here, we're going to read the little accept thing that they just sent. And that's going to be placed right into read buffer 0 because this read buffer function will write that into read buffer 0. We're going to check if it equals y, then do all this stuff. And else, if I can spell else, we're going to say, we're going to std cout the server refused the connection. Actually, I'm going to say this a little bit fancier. Watch this. I know you guys are getting jealous at my C++ skills right now. Ooh, watch this. The server at socket remote endpoint there we go. There you go, very simple. So the server at socket.remote endpoint refused the connection. That's because in any other case where they did not send y, they most likely refused the connection. And then if they refuse the connection, we are going to call socket.shutdown and socket.close. Right there. And there we go. That should properly be good. We also are gonna print out something right here. Accepted the connection. Wow. So cheerful with the exclamation mark. All right, let's run this now. This man is going to host. This man is going to join and type IP address 10.0.1.4. Do you want to accept this connection? Yes. And that accepted the connection, and that's because it's in a while loop. Okay, I should probably push that out of the while loop. Why is this getting angry? Bruh. I should be perfectly happy. Is it because of this if? This if. Wait, why wasn't I yelling previously then? Oh, this if doesn't even have a body. At all. This if just had the while as its body. That's crazy. Now this if needs this. Now we're good. So it still has build errors. Link.exe exited with code. Cannot open. Oh, that's because this program is open. That's all that happened. So after all of this, finally, what we can do is press host, press join 10.0.1.4, and I can say yes. And now I can type. And I didn't even put an end line manipulator on cout. But yeah, you get the point right here. This cout right here, dot right, probably should have a. There we go. This program now, it allows us to, sufficiently for our purposes, also we don't really need the system pause anymore because all of them are stuck in while loops by the end of the program. This program now, though, efficiently lets us accept connections. And I feel like I could make this code a little bit cleaner by like changing around the spacing and such. But I couldn't care less. We can now sufficiently for our purposes, securely, relatively speaking, accept connections. Now, I'm not a security expert, so if you start opening sockets on your computer and start listening to data on certain ports and just get sent malware, then that's not my issue. But this, for the type of purposes that I'm using, should sufficiently allow us to, for example, write a game application that uses this type of data. And speaking of game application, I think I have something like that. So let me go find it. So right here. Right here. And this is not actually a great program. This is actually a pretty terrible program, if I'm gonna be honest. But I wrote this program earlier. Let's press host for this guy. It's asking for network access. Press join on this guy. 10.0.1.4. And this opens because this guy is ready. Press yes on this. Now this guy opens a window. And I don't have it as sophisticated as the program I just made, as you can see. But what this program allows you to do, oh, come on. I kind of have to take that call. Well, this program, all it lets you do is draw onto the screen, and it looks terrible because very low FPS. I don't know why this one has so much more FPS, and now this one has more FPS. So those were pretty bad. Well, I missed that call. Let me go call them back. If you want to know how to very nicely and easily zoom in and out on Visual Studio, it's just Ctrl and then mouse wheel. Lets you zoom in all the way here where I see define asio standalone. But right here, here's our code. We're gonna save this, and we're gonna take a look at that program that I just showed. So, all right, so here we have our project, and this is uses a whole bunch of different stuff, and it's kind of messy. It's split into a bunch of different functions because I was testing stuff. But down here, we're going to go down here and we're going to check what is going on. What is the new stuff that we have to learn to figure out how this program is working? If we remember correctly, this was the program that let us create a that let us draw on a game. So I'm actually going to set this to release mode instead of to 64-bit because why not? And we're going to start it. And that worked. Okay, so let's get rid of some of these. Go to here, and let's go to x64 release demonstration.exe. So now that we have two exes, we can press H to host on one, J to join on one, 10.0.1.4. This guy is going to be yes. Now we have two separate things. We can draw on this, and it appears on this. I don't know why though, when I draw, the FPS immediately shoots down. Or the FPS is only high for some reason right now on the one that I'm not looking at. Look, this one is 1700 FPS. And once immediately I switch to it, it's 60. Is it? No, it does not have VSync on. So I don't know what's going on with that. But that program, as you can see, it lets us draw dots and send it between two instances of the program using asio. How does this work? Well, we create first initially right here. We're going to skip over this idle work thing for now. Let's create this this std thread context. So this std thread is probably normally to get an std thread object, you include include thread, and you get std threads. But presumably one of those header files up here already included thread, and so I didn't have to. If we go down here, what we're going to see is that we have an std thread object called thread context, and it is equal to this very strange looking statement right here. Now, a thread, what it does is it takes a function as its parameter, and it runs that function in parallel to the function that calls it. So the main, or not actually the main function, some other type of function is going to call this. But, oh, actually, now that I see what's going on here, well, it runs this function in parallel to whatever function called it. And so this is going to run two separate functions at the same time when you create this std thread. And you see here's its parameters, and we pass into its parameters this thing. And now this thing that we pass into its parameters is actually a function right here. And this is what's called a lambda function. So for a lambda function, what that means is it's just a mini little function that we're creating on the spot right here to usually just to pass into something as a function parameter. We create a lambda function to allow that to happen. We could create a separate function and just manually assign it there, but we're creating a lambda function right here. And this lambda function has the syntax of first having a box like this. I'm not super detailed in how lambda functions exactly work, but you, inside of this box initially right here, you say whether you want to pass in stuff as a copy or a reference. And right here, we're passing stuff in as a reference. Right here is the list of parameters. So if you had parameters for this lambda, you would put like int a, int b, something like that. The last thing right here, this is the function body. Remember, C++ is free form, so you can just put the function body right after the function, right, like this. Inside this function body, all that's being called is context.run. Context.run is this IO context object right here, and we're calling it run within a separate thread. That means that this asio IO context pretty much will be running within a separate thread. So it's going to be running separate from our main program. So everything that goes on inside of that IO context will pretty much be separate from our main program. So to recap, we have a std thread object which takes a function as a parameter, and the function that is its parameter is this lambda function right here. And the lambda function, all it does is it calls context.run, and so that makes it so context the IO context is now running within a separate thread. Okay, right here, all we do is we grab a socket just using this def asio function, which I created for testing purposes mostly. And all the def asio does is it just goes through and it creates us a socket with a proper connection. Now right here we have a v buffer, and this is a std vector of chars, and it's a buffer, and we're setting it equal to an std vector of chars with 8 chars inside of it, because when we pass an 8 to a vector constructor right here, we're constructing a vector with 8 default chars. So right here we have the received pixel, which is just a just a pixel. It's just a pixel. If you think about how this received pixel is structured, it has 2 integers right here. And so what happens is those 2 integers, if you think an integer is exactly 4 bytes, and so that means that one of these would fit inside of this vector buffer right here. So we could change this in this vector buffer into a received pixel. We could copy the contents of a received pixel into the vector buffer, and I copy the contents of a vector buffer perhaps to a received pixel. Right here we also have another variable called send. Now this was all pretty much like this was all kind of like test code for me, but it works, so I'll demonstrate how it works. And we have another char array right here called send, and this is used for the pixel that we're currently sending, because every single time we create a pixel, we want to send it to the other guy so he can also display this pixel. And right here, right back up here, we have this idle work object, and it's of type asio IO context work, and we set it equal to asio IO context work with context passed into its constructor. And so what this does is it kind of just binds the idle work object to the IO context, and so that makes it so the IO context does not what is it called? Does not just exit when it has no work to do. This gives it some idle work to do, so it stays around instead of exiting after it finishes all the work that it's done. So when we go up now, what we can see, these are all miscellaneous functions. This is the acceptor. Now here's where the goodies are. We have this void grab function. And where's this grab function called? Well, this is called within the game logic. This is the entire game logic, by the way. This just says pixel.x equals mouse get x. So we're just setting the pixel x vertex to the mouse x, and then the y to the y. We're adding that to the pixels pool. Then what we do is we copy to our send variable. So we use as the destination our send buffer right here. So we created a buffer called send. And then we use as the source, what are we going to copy into the send? We're going to copy the pixel that we just created right here, pixel, and we're assigning pixel.x and pixel.y. So we copy the contents of this pixel, we put it into the send buffer, and we say copy up to 8 bytes because that's the size of this pixel in the send buffer. Right here, we're just going to do socket.writeSum. This is the writesum function we're familiar with. Send 8 because we're sending 8 bytes. And I think about it, I don't even think that 8 is necessary. No, it's not. But I'm going to keep it. And then right down here, we just draw the pixels very simply. What else should I check? Oh, if we check on the onUserCreate function, we do one thing here. Now this onUserCreate, if we remember, is called once on the first time that this program is created, and all it does is it calls the grab function, and the grab function is down here. This is really the meat of the program, the grab function. And it looks a little bit intimidating, so let's see what's going on here. Well, it returns nothing. All right, it takes an asio TCP socket object, and we did pass it a socket right here. It takes a vector that takes a vector of pixels right here, OLC vi2d, and we're using those vi2d objects to represent our pixels. So this is a vector of pixels pretty much, and we call it pixels pool, and we're passing in a vector of pixels called pixels pool to it. Very nice, very simple. Now what we do is we say socket.async read sum. Now this is very similar to the read sum function, except what happens is that this read sum function is performed, it's performed asynchronously. So this read sum function is not only performed once. This read sum function is, it waits until there's data to read, and then it reads that data. We don't have to put this asynchronous read sum function within a loop or anything like that and constantly check. We just use this asynchronous read sum function to read data when data arrives. And so it takes a few parameters. It takes, first of all, a buffer, and that buffer takes some parameters, right? vbuffer.data gives us a pointer to an array of chars, which is our, well, actually not an array of chars. This just takes a pointer to an array of OLC vi2d. But that buffer doesn't care. It cares about taking a pointer. So right here, we can put vbuffer.data to have our buffer placed in. Then how many do we want to copy into, or how many bytes do we want to copy into that buffer? Well, we want to copy bytes equivalent to the size of the buffer, so that would be 8 bits, or 8 bytes, because 2 integers, 4 bytes each, that's 8 bytes. And then it actually takes one more parameter. So it takes initially this, the read sum function, the regular read sum function, took in a buffer object like this, except the asynchronous read sum function takes in a buffer object as well as something that is generally called a handler in code. And handlers are just handlers in the context of code are usually just functions that handle some type of operation. In this case, the operation that we're handling is reading the data. So what happens here is the handler function that we're passing into it is actually just another lambda. So this lambda right here is takes in references, and it has one parameter, error code, and it has one parameter, size t. So right here, this is a standard library error code that it has right here. This is a size t that it has right here. And you can see, well, how are we passing in these parameters? Well, if we look at the async read sum function, the async read sum function, when it's looking for a handler, it expects the handler to have these types, and it passes this in to the handler. It expects the handler to have 2 parameters of these types, and it passes everything into this handler right here, this handler function. This handler function will go off and do whatever it wants to do with whatever the async read sum function just did. So the async read sum function, in this case, if we recap, it waits for some data to appear, and then it it writes that data into the vbuffer, and then it writes up to an amount equal to vbuffer.size. Then it calls a handler to handle that data that it just read, and that handler has to have a std error code object and a std size t object called length. So right here we have a handler function, which is just a lambda, and it has those two parameters that get passed into it from the async read sum function. Right here, within the handler, what we do is we define something called received pixel. And now that I'm thinking about it, I could have probably defined this outside of this or something like that. But inside this handler function, we initialize a variable called vi2d. If we remember, we're using vi2d in our program to represent a pixel because a vi2d can hold two integers, so x and y position. And then it says if not error code. So error code returns true if there was an error. So if there's no error, then the way that error code would check if there's an error or not is this async read sum function presumably passes in an error code into this this handler right here, and that's how this error code right here is checked of whether it has an error in it or not. So we're saying if there's no error, then we use memcopy again. So we copy the contents of vbuffer.data, which we just read right here, to received pixel. Received pixel is our pixel that we just made right here, that we just initialized, and then we copy it up to the length. The length right here is a size t equivalent to the amount of data that was read by the async read sum function. Then after we copy the data, so what we do is we receive some data from the async read sum function, we copy it into the received pixel right here, then we push that into the pixels pool, and then we call the function again to check if there's any more data to grab. So actually, I'm not sure why this does not have like a really bad recursion problem, because we're going to be calling this function over and over again, presumably. So I don't know why there's not like some serious recursion happening, but whatever. And if we check, this function actually right here is literally just a single parameter within this async read sum function. The end of the async read sum function is right here. And if you're experienced in C++, you're going to see that I made a crucial mistake right here. And that is the fact that when using this grab, or when doing this pixels pool dot pushback function right here, I did not put a lock. And that means that I pretty much could just crash my program because there's no lock. And the reason for that is, if we remember, this socket right here is, if we check down here, well, actually that socket is just made through my own function. But that socket is bound to this IO context object right here. This IO context object is running in another thread. Remember, threads run parallel to the program. So this async read sum function is not only asynchronously reading data, it is also running in another thread. So it's a much more complicated setup than what we previously had. What that means is that this is running in parallel to our game logic right here, which is on user update. So because of that, what that means is that if we check right here, it says pixels pool.pushback. Well, what is pixels pool? Pixels pool is something that's passed into the grab function right here, pixels pool. Where's that pixels pool defined? It's defined right here. And you can also see right here, we're doing operations on the pixels pool. So this onUser update function is running at the same time as this grab function because they're running in separate threads. And if we check right here, this pixels pool, if we see, has an operation dot push back onto it. This pixels pool is being added onto at the same time as this is trying to add onto the pixels pool. What happens if, for example, both of these try to write something to it at the same time? We don't know. There could be a crash. There could be just a pixel that goes missing. I'm not sure exactly. And that's when you would want to make sure that only one thing can write to an object at the same time. And I think a way you might actually be able to do that relatively easily is you do something like, let me check if I can figure this out. I think we can do std scoped lock, and we also need one more thing. Std mutex m. And I'm not sure if that's actually all you need to do. This might literally be all you need to do for this to work. So what happens here is that we're creating an std mutex object right here. And this std, oh, actually, now that I'm looking at this, I don't really like this. I feel like this might mess some stuff up. And so I think what we might want to do is, I'm not sure if this is possible or valid, or maybe it's just frowned upon or like bad code, but I think technically we could do something like that, right? Just put that in its own scope, unnamed scope. Why not? If you know if this is bad code or something like that, I know this entire program is bad code, but if this in particular is bad code, then you can tell me in the comments. But what should be happening here now is this is what's called a mutex, and a mutex is an object that locks other objects so that only one thread can write to the object. So that means if an object is locked by a mutex, one thread is going to have to wait for that mutex to be unlocked for to be able to write to it. So the way that we lock the object is we created a mutex right here, and this scoped lock function, for our purposes, it's very, very simple. There's some more primitive ways to do this, but this scoped lock is really quite nice because it finds a scope that you're inside of. So right here, this is a scope, and it locks a specific mutex, and anything within that scope is now locked under that mutex. So this pixels pool object is now being locked by this mutex right here that we created right now, and it's only locked, so it is locked once this scope lock is initialized right here, and then it is unlocked at the end of this scope right here, which is at the end of this block. And so when you run this, it's going to be locked. The pixels pool vector is now locked whenever we write to it with this thread. And so when the next thread does its operation, it has to wait for it to be unlocked for it to do its operation. And you know, it may only be locked for a fraction of a millisecond. So it is usually not such a big deal locking objects, but especially in a case like this. There is cases though where you could lock an object, and if you don't unlock it for a long time, then your main thread would be stalled. Your main program would be paused because it's waiting for an object to be unlocked. So right here, this scope lock though will lock the object inside of the objects inside of its scope when it's initialized, and then it'll unlock the objects once it goes out of scope, and it goes out of scope at the end of this block that we just created right here. So this now is in release x64 mode. So this guy should be able to join now. This guy should be able to, or that guy should be able to host. This guy should be able to join. All right, run that. Accept. And I don't know why FPS is locked to 60. But theoretically now, there should be no issues with both of these guys trying to write to the same vector. Because whenever this guy is writing to a vector, this guy is going to be paused, and vice versa. So there should not really be any issues. Now this program used to run much better, but for some reason when I click on it, I don't know, some type of VSync is going on or something. It may be that I need to go to NVIDIA control panel and turn off G-Sync or something. Let's attempt that. Enable for full screen mode. And I guess let's also restart these programs. I don't know if this is gonna work. Let's go here. So this guy's gonna host. Oh, it's still 1800. Looking good. Looking good. This is still 1300. Now, there we go. We got some nice looking bold lines. I tried this on, like I sent a version of this program to my friend, and he attempted to check if this program was working. And he could draw and I could draw, and it was all nice until we drew at the same time, and then the program crashed for me because we had some type of conflict because the threads tried to write to the vector at the same time. Right now though, you can see the FPS slowly going down. This is what we like to see. Like you can see the lines are even getting sometimes a little bit more spaced apart. Okay, so I'm gonna close this and close that, and I'm gonna call that the end of this video, unless I can think of something else. Let's go here. If you got questions or something, leave them in the comments. Of course, I'm an expert C++ coder. If you guys didn't know, I've been doing this for like 4 weeks now. So yeah, like I'm pretty much an expert at this. So you guys can just leave those questions in the comments for me.